Good evening. Can you hear me? Yeah. Okay. So let's get started. Determine the poles of the circuit. Neglect all other capacitances. Determine the poles of the circuit, the pole frequency or cutoff frequency. Poles or cutoff frequency. So in the exam, only one capacitor will be given, and the examiner wants you to find the cutoff frequency due to that capacitor. Determine the poles of the circuit. Okay. Venkat, video.
Hello,
Venkat,
sir.
video off చేసినట్టున్నా.
నేనే ఆఫ్ చేయలేదు సార్, మీరే ఆఫ్ చేస్తున్నట్లు చూడండి.
కరెక్టే, హోస్ట్ ఇప్పుడు మళ్ళా వచ్చింది. Okay, so determine the poles of the circuit, neglect all other capacitances. Let's solve it. Now, what is the input resistance of the gate current? Here is 0. So it is an open circuit. And you have RG here. Your Vin is also shorted for calculating the resistance. The voltage sources should be shorted. So RG and C1 are in parallel. So what is tau? Tau equal to RG into C1. Then what is the pole frequency or the 3 dB cutoff frequency? It is equal to 1 by tau. It is 1 by RG into C1. It is 1 by RG into C1. Now, if you want in hertz, what you can do? If you want in hertz, F3 dB, it is 1 by 2 pi tau. It is 1 by 2 pi RG into C1. RG into C1, right? So this is the pole frequency or the cutoff frequency. So how do you calculate the time constant tau? Tau is R multiplied by C, and omega 3 dB is 1 by tau. So similarly for this problem, now we are avoiding the high frequency analysis, right? Yesterday we have done with the high frequency model. Now we are trying to avoid it because we already know what are the resistances at each of the terminal. So intuitively we are trying to solve. Now for AC analysis, VDD is ground, and here you have R naught. So you have two resistors now, RD and R naught. Here there is a capacitor, C2. Suppose if this is node A, from A to ground, there is R naught. From A to ground, there is RD. And there is a capacitor. So how are these two resistors, RD and R naught? They are in parallel. Therefore, tau is equal to RD parallel with R naught into C2. And what is the pole frequency or the 3 dB cutoff frequency? It is 1 by tau. It is 1 by tau. So RD parallel R naught into C2, and the pole frequency or cutoff frequency is 1 by tau. Now, if you have a capacitor between the input and output, an ungrounded capacitor, then this is going to set up two poles, two cutoff frequencies. And one is from the node 1 to ground, which is C1, and the other between node 2 to ground, which is C2. Now, this is the combination of the first two problems here. The first two problems had C1 from this node to ground and C2 from this node to ground. And this single capacitor is going to set up two poles, C1 to ground and C2 to ground, right? And what is the value of C1? C1 is going to be CF into 1 minus V2 by V1. 1 minus V2 by V1. And C2, what is V2 by V1? What is V2 by V1? For calculating the gain, we have to replace capacitors with open circuit. So this is V2, here V1, and here you have RD. What is V2 by V1? V2 by V1, this is the common source amplifier. The gain is minus GM into RD. The gain is minus GM into RD. So now, for this, it is CF multiplied by 1 plus GMRD. What about C2? C2 is going to be CF multiplied by 1 minus 1 by V2 by V1. So V2 by V1 is GMRD minus GMRD. So this is approximately CF. Because a large value in the denominator, you can neglect. A large value in the denominator, you can neglect. It is approximately CF. So C1 and C2 are known. Now, this circuit has turned into the first two problems now. First two problems. You have C1, there is RS. You have C2 here. And this is RD. And you have R0. So two poles. A capacitor in the middle is going to set up two poles, omega P1 equal to 1 by tau RS into C1. Omega P2 is going to 1 by RD parallel R0 into C2. 1 by tau. And what is C1 and C2? Where C1 is going to be CF multiplied by 1 plus GMRD, and C2 is CF, right? C2 is CF. Therefore, omega P1 is going to be, or omega 3dB, 1 by RS into CF multiplied by 1 plus GMRD. This is the pole frequency at the input side. What is the pole frequency at output side? 1 by RD parallel R0 into C2, right? So we just substituted here, nothing great. So orally also you can do it, right? So this capacitor C1, this is C2. What is C1? CF multiplied by 1 minus V2 by V1. What is V2 by V1? Minus GMRD. That is C1. C2 is approximately CF. So Miller effect is seen at the input side, not at the output side. Is it not? Not at the output side. This is only the calculation of gain. Calculation of gain. So this is how we can calculate the poles. Yesterday we have done for BJT, right? By using all the capacitors, but generally in exam, they will give only one capacitor and ask you to find the cutoff frequency or the pole frequency. So this node is V1 and this node is V2. Where the capacitor is connected, left plate is at V1, right plate is at V2. Don't calculate for overall gain of the amplifier. See where the capacitor is connected. Left plate is at V1, right plate is at V2, right? never consider RS for gain, is it not? Because this is the gain experienced by the left plate of the capacitor to the right plate of the capacitor. Now, what is M2? What is M2? It is a diode we have seen. This is equal to 1 by GM2 parallel with R02. 1 by GM2 parallel with R02. Here you have CL and this is R01. So these two are in parallel, is it not? So 1 by GM2 parallel with R02 is approximately 1 by GM only. So what is tau? Tau is R equivalent into CL. What is R equivalent here? It is 1 by GM2 parallel with R02 parallel with R01 into CL. But in exam, you know, R0 he might neglect sometimes. If he neglects, if R0 is infinite, then it is going to be CL by GM2. It is approximately going to be CL by GM2. Then what is omega 3 dB, pole frequency? It is going to be 1 by tau. 1 by tau. So it is going to be GM by CL or GM2 by CL. So examiner likes, you know, numbers like this, GM by CL, simple numbers. So he might neglect early effect. If he does not neglect early effect, you can take R0. What is it? Right? Because 1 by GM is in tens of ohms and R0 is in mega ohms. So mega ohms parallel with 10 ohms. There is no comparison at all. It is approximately 1 by GM only. So remember, whenever we are calculating gain, the frequency response plot for shunt capacitor is something like this, is it not? Something like this. At this point, we are calculating the pole's upper cutoff frequency. At this, that means in the mid frequency range, what is the behavior in the mid frequency range? All the coupling capacitors, series capacitors are short and all the parallel capacitors are open. So these are shunt capacitors, parasitic capacitors. So you have to treat them as an open circuit for calculating the gain. This is the maximum gain that you get, right? So for calculating gain, please replace capacitors with what circuit? Open circuit, and make it a simple circuit without capacitors, right? If you short capacitor and find, then your answer will become 0, is it not? If you just short the base and collector junction, wherever capacitors are there, don't short them. For calculating gain, coupling capacitors should be short, parasitic capacitors should be open. So whenever you're doing, all these are shunt capacitors. Shunt capacitors means open circuit. So you just open circuit and calculate the gain, right? That is why whenever I teach, first basic I will teach 5 minutes. After that we'll do problems. That 5 minutes you have to see 10 times and then you have to go for problems. So whenever we do problems and you don't, first 5 minutes, whatever I teach, frequency response table, coupling capacitor bypass, if you don't look at that, doubts will keep on coming. Are you getting? So first 5 minutes, just basics we will teach. That after the lecture is over, you have to revise, you have to see, right? Every point you have to analyze, think, is it not? So the gain is constant in the mid frequency range. So at that point, we have to calculate the gain. So coupling capacitors are short, parasitic, all the shunt capacitors are open circuit. You open circuit and calculate the gain. If at all you want gain. If you already know the gain of a common source amplifier minus GMRD, then it is not needed. So similarly, what is this terminal? Drain. This is also drain. So what is the resistance seen through drain? It is going to be R02. Here it is going to be R01. You have CL. So what is tau? Tau is going to be R equivalent into CL. R equivalent is R02 parallel with R01 into CL. Then what is the pole frequency? It is always 1 by tau. 1 by R01 parallel with R02 into CL. This is the cutoff frequency or the pole frequency. So such questions are given for 2 marks, right? Okay. Now, just for a change, I have given BJT. So now we are not going to draw the high frequency model. We are going to do this problem intuitively. Otherwise, two transistors you have to draw with the high frequency model and then the capacitor, right? Okay. Now, what is the resistance? What is the name of this terminal here? At this point, there is some resistance here, and of course, there is some R01. What is the resistance seen through emitter, right? If the examiner gives you VA equal to infinite, then you don't have to consider R0. Your R0 also will become infinite, right? Okay. Tell me, what is the resistance seen through emitter here? Rx. Rx is going to be alpha by Gm. If you go from emitter to base, the resistor should be divided by 1 plus beta. So this is Rx here, right? And this comes in parallel with, at this node, you have Rx from here to ground. And here you have R01. And then C. So what is R equivalent? R equivalent is going to be alpha by Gm plus Rb by 1 plus beta in parallel with R01. If the examiner says early effect is infinite, then it is only alpha by Gm plus Rb by 1 plus beta. Small value, is it not? And what is tau? Tau equal to R equivalent into C, and the pole frequency or the 3 dB cutoff frequency is 1 by tau. The 3 dB cutoff frequency is 1 by tau. So you can substitute now. What is tau? Tau is this value, R equivalent into C. So omega is always 1 by T. F is 1 by 2 pi T. F is, omega is 2 pi F. Omega is what? 2 pi F. If you want in F, what you have to write? F is 1 by 2 pi T. 2 pi T. What is T? It is alpha by Gm plus Rb by 1 plus beta into C. So please don't forget, omega is nothing but 2 pi F. Omega is 2 pi F, right? Omega is 1 by T or 1 by tau. Omega is 2 pi F or 1 by tau. So what will be F? 1 by 2 pi tau. 1 by 2 pi tau. Okay. So what is the Miller capacitance here? C input. C input is the capacitance from here to ground. What is C in? And the output, this is C output here. This is C output. We don't want C output, we want C input. So what is C input? It is going to be CF into 1 minus V2 by V1. CF into 1 minus V2 by V1. What is V2 by V1 for this? For this circuit, we have already calculated V2 by V1 is going to be minus GMR0. So it is CF into 1 plus GMR0. CF into 1 plus GMR0. If you want, we can calculate here. This is V1, V2. So V2 by V1 is minus GM into RC parallel R0. RC parallel R0 But RC is infinite. Current source is there. Minus GMR naught. It is minus GMR naught. This is the gain. So your answer is going to be CF into 1 plus GMR naught. This is your C in. This is your C. This is your C. CF into 1 plus GMR naught. Now, what happens if the gain is negative? If the gain is negative, you're going to simulate a positive capacitance. What happens if the gain is positive? If the gain is positive, then you will simulate negative capacitance. You're going to simulate what? Negative capacitance. So according to Miller effect, so what does Miller effect says that Miller effect, if you have an amplifier and V1 and V2, and if you connect an impedance Z here, Z, then what is Z1 or Zin here? It is going to be Z by 1 minus V2 by V1. V2 by V1. Or R is going to be R by 1 minus V2 by V1. And what is C? C in is going to be C into 1 minus V2 by V1. So from here, we know that if V2 by V1 is negative, then C in is positive. Capacitance is positive. If V2 by V1 is positive, then your C in is going to be negative. So you are going to simulate a negative capacitance. So if V2 by V1 is negative, then your C in is positive, R in is positive, C in, R in, comma, C in is positive. If V2 by Vn is positive, then R in, comma, C in is negative. R in and C in are positive, so R in and C in are negative, right? Okay. Now, what about this amplifier? The name of this amplifier in BJT is emitter follower. Emitter follower. That means the output at emitter follows the input. That means its gain is 1. Its gain is 1, right? The output at emitter follows input. But here, this is gate and this is source. And the drain is grounded. So this is a common drain amplifier. Common drain. Common collector amplifier is called emitter follower. Common drain amplifier is called source follower. It is called source follower. So what is the gain of a source follower? The gain of a source follower, this is suppose V2, V1. So V2 by V1 is going to be 1. V2 by V1 is going to be 1, right? Because common drain or common, this is like common collector, right? Now, what happens if somebody puts a capacitor here? Capacitor. CF. Then what is C in? C in is going to be CF into 1 minus V2 by V1. V2 by V1 is 1. So your CF into 1 minus 1. So what is 1 minus 1? 1 minus 1, if you subtract 1 with 1, it is 0. So your input capacitance is going to be 0. Your input capacitance is going to be 0. So this CF experiences bootstrap. CF experiences bootstrap. So we have seen this yesterday with the common collector amplifier. So there is no Miller effect for common collector. No Miller effect for common drain or common collector amplifier. No Miller effect for common drain or common collector amplifier. So your CF is going to experience bootstrap, right? So simple questions can be framed like this, right? It's not like You have to draw the whole high frequency model. Capacitor here, capacitor there. What is input capacitance? What is output capacitance? What is the time constant? What is the pole frequency? Right? Now, this is not a parasitic capacitor. In my 9th problem, there is no parasitic. I have intentionally connected a capacitor to a common base amplifier or to a common, what is common base here? It is common gate amplifier. And what is the gain of common base? The gain of common base is GM into RC or GM into RD. That is a positive gain. So when a capacitor is intentionally connected between the input and output, then this capacitor, because the gain is positive, you're going to simulate a negative capacitance. You're going to simulate a negative capacitance. So let us solve this. So first, we should know the gain of the amplifier, right? You have to just remove the capacitor and see the gain. And please mind you, the gain is only from left plate of the capacitor to the right plate. So it so happens that the right plate of the capacitor is V0 and the left plate is Vin. It is Vin. So what is V0 by Vin? V0 by Vin is going to be GM into RD. It is going to be GM into RD. So this V0 is V2 and this Vin is V1. V0 is V2 and Vin is V1. Now, you connect a capacitor here. When you connect a capacitor, then what is your Cin? Your Cin is going to be the CF multiplied by 1 minus V2 by V1. Now what is V2 by V1? It is GMRD. So it is going to be CF into 1 minus GM into RD. Suppose your GMRD is 100, right? 100. What is 1 minus 100? 1 minus 100 is minus 100, is it not? It's 99, but okay, 1 you can neglect. So 1 minus 100 is minus 100 only. So this is approximately minus GMRD CF is Cin. It is minus GMRD CF. So when a capacitor is connected to an amplifier whose gain is, capacitor is connected to an amplifier whose gain is GMRD, and here there is a capacitor, CF, right? So this is V1 and this is V2. Then what is the input capacitance Cin? The input capacitance Cin is going to be CF multiplied by 1 minus V2 by V1. It is going to be minus GMRD CF. Right? So if V2 by V1 is positive, then your Cin is going to be negative. If V2 by Vn is negative, then your Cin is going to be positive. Are you getting? Okay. So yesterday I mentioned that this is the frequency response plot. Am I right? In this frequency response plot, now you are calculating the pole frequency here. In this, the gain is constant here. In this mid-frequency range, all the coupling capacitors are series capacitors. Coupling capacitors are short. Shunt capacitors, parasitic capacitors are open, parasitic, open circuit. That means all the Miller capacitor, shunt capacitor means Miller capacitors, and the capacitors at the input C1, C2, right? So these are all open circuit. Then your gain will be maximum. So while calculating the gain, you should always see that the parasitic capacitors or shunt capacitors, Miller capacitors are all open circuit. Make it a capacitor free circuit. Make it a capacitor free circuit. Don't directly short the capacitors while calculating gain. If you short, your V2 by V1 will always be 0. Is it not? There is no question. Yeah, where did we stop yesterday? Yesterday I told you that our main aim is to build a wideband amplifier, right? Common emitter suffers with Miller effect because of the Miller multiplication, right? So yesterday we have seen, yesterday's class we had a common emitter here, am I right? Common emitter. Common emitter. And what is the high frequency analysis that we have done? High frequency analysis. Because low frequency, it is only for time pass, I told you. Low frequency cutoff frequencies are not going to decide the bandwidth. The device junction capacitors, parasitic capacitors are going to decide the bandwidth. So we had a capacitor here, which is C pi. And we had one more capacitor here that is going to be C mu. So now we split this capacitor as two capacitors, right? We split this capacitor as two capacitors. So this is the summary of yesterday's class. We took so much time in doing this, but today, because our mind is trained now in all the tau calculations, see how easily we will do it now, right? The C mu here is going to be C mu multiplied by 1 plus A, or 1 minus V2 by V1. V2 by V1 is GMRC. And here you are going to have C mu. So what is tau 1 and what is tau 2? Tau 1 and tau 2. Tau 1 is going to be RS parallel with R pi. There is RS parallel with R pi between base and emitter, right? RS C pi. There's some capacitor C mu into 1 plus GMRC, right? Or you can call it C1. This is C1. Here there is R1 or R pi, right? R pi into C pi plus C mu multiplied by 1 plus GMRC. So how did you calculate gain? Gain calculation is from left plate of the capacitor to right plate. So this is going to be our common emitter amplifier. So the gain V2 by V1 is going to be minus GM into RC. So 1 minus, this is C mu into 1 minus V2 by V1. All right. So when you substitute, you will get C mu into 1 plus GMRC. So this is tau 1. What is tau 2? It is RC parallel with R0 into C mu. So what is pole frequency omega P1? It is 1 by tau 1. Pole frequency omega T2 1 by tau 2. But if you want overall bandwidth, what is the overall bandwidth of the system? It is going to be 1 by tau, which is 1 by tau 1 plus tau 2. The total delay offered by the system is the delay offered by individual poles, right? Or if you want to separately calculate, tau 1 is 1 by omega P1, tau 2 is 1 by omega P2. You can do it, right? So this is your bandwidth. So this is 1 by omega P1. So this is the summary of yesterday's class and yesterday's class, right? So you can see the big value here, the big value of tau1 here, right? That C mu is multiplied by 1 plus GMRC. So what happens if tau1 increases or if tau increases, then the bandwidth is going to suffer, right? The bandwidth is going to suffer. So common emitter amplifier suffers with low bandwidth because of Miller effect, Now what I'm going to do now is, this GMRC is there, no? That GMRC, I want to make it 1. So if GMRC is 1, 1 plus 1 will be 2. So 2, that's all, only 2 C mu. Then your tau1 value will be small, chota tau1. Chota tau1, bada bandwidth, right? If your tau is small, bandwidth is going to be large because bandwidth is 1 by tau. Bandwidth is 1 by tau. Tau should be made chota. So how can you make tau chota? The gain has to be small. If you make gain small, tau will be small. Tau is small, bandwidth will be large, right? So let's see how to make it tau small. For that, we have to go for cascode amplifier. Cascode. So what is a cascode amplifier? It is common emitter with common base. The common emitter with common base. Common emitter with common base is cascode. So with this structure, we can have wider bandwidth. Cascode is a versatile structure. Number one structure of all the circuits in electronics, the number one structure is the cascode structure. Without this structure, there is no integrated circuit. You take any analog IC, any communication IC, you see the internal diagram, some sort of cascode will be there, right? Without cascode, there is no analog, right? Cascode structure. This is a wide band amplifier. Wide band amplifier. Wide band amplifier. So what is the advantage of this? Advantages. Advantages. The advantage which we already discussed is, one is high output resistance. High output resistance. If you treat RC as the load, then what is R0? Seen downwards. So here you can have a R02, right? This is R02. And here you have R01. So R02 plus 1 plus GM2 R02 into R01 parallel with R pi 2. So this is something I have already derived, right? So R01 plus 1 plus GM2 R02, GM2 R02 into R01 parallel with R pi 2, right? So it's got high output resistance. And what is R0 parallel with R pi 2? This is approximately R pi 2. So it is R02 plus R pi 2 plus GM2 R02 R pi 2. So now what happens, right? This R pi 2, GM into R pi is beta. So it is this R pi 2 you can neglect, R02 plus beta times of R02. Or it is 1 plus beta times of R02. Beta is large value, beta R0, you can say. Beta is large value. So your R0 is going to increase to beta times beta times, right? If it is a MOSFET, it is GM to R02, R01, something like that, right? So your R0 is going to increase how many times? Beta times. Beta means beta is 100. Typical value of beta is 100. 100 times your output resistance will increase. High output resistance. Right? Second advantage is no change in gain. No change in gain. So what is the gain of a C amplifier? The gain of a C amplifier is minus GM into RC. Gain of cascode is also same. Why? Because the overall transconductance of cascode amplifier is equal to the larger transconductance of C amplifier. Therefore, the gain AV is equal to still minus GM into RC. The gain AV is still going to be minus GM into RC. So how it is minus GM into RC? I told you what is a simple shortcut for this. We have E in here. V naught. So imagine a single current here, IC, right? This VB. So what is V naught by V? It is minus of some value. Your output is across RC and your input is VB here, 1 by GM. So this is going to be minus GM into RC. But if you want R0, there's a big R0 here lying, and that parallel with RC is RC only, right? A large resistance parallel with a small resistance is going to be RC. So there is no change in the, see, simple. The current is still same. Q2 and Q1 current is still same. Your output resistance is RC and your V in is across VB. So the gain is still same. So this is such a versatile device that bandwidth will increase, gain is going to be same, and output resistance also will increase. So that means it will somehow increase the gain bandwidth product. It is somehow, that means analog engineers, they're thinking off the box, right? How to increase the gain bandwidth product. To increase the gain bandwidth product, gain still remains same, but the bandwidth of this circuit will increase. The main So let me repeat, there is no change in the gain and the output resistance has increased. Now, the most important thing now is, how is that the bandwidth has increased? How is that the Miller capacitance has decreased? Now just focus on the Miller effect capacitance. It is the Miller effect capacitance. Oh, so. Now, can you see here, there is the Miller capacitance here, CF. Previously, what was the capacitance at the input? If there is no common base amplifier, this is a common base amplifier. This is the common emitter amplifier. Why is it called common emitter? Because emitter is grounded. Emitter is grounded. Why is this called common base? Because base is grounded. Base is grounded. So common emitter connected to common base is called cascode. So you can see here, in a common emitter, input is given at base, output is taken at collector. In a common base, input is at emitter, output is at collector. Input is at emitter, output is at collector. So you can see here, collector of one transistor is connected to emitter of the other. Collector is connected to emitter. Okay, so there's some problem with the connection, I believe. Fine. Can you hear me now? Can you hear me? Can you hear me? Okay. Fine. I was trying to say that the gain remains same, but the bandwidth they are trying to increase. Don't think gain bandwidth product is constant and all that. The gain bandwidth product is constant only for negative feedback circuits, right? With feedback and without feedback, if you see the open loop gain and bandwidth, for op-amp, open loop gain will be very high, open loop bandwidth will be very small. After giving negative feedback, what will happen? The gain is going to reduce and the bandwidth will improve. But if you want to improve gain bandwidth product, there is only one technique to improve the gain bandwidth product. That technique is called cascading. That technique is called cascading. Cascading is the only technique where you can improve the gain bandwidth product of the overall amplifier. So what is an amplifier for me? The two stages together is an overall amplifier, and definitely we are going to improve the bandwidth. How we are going to improve the bandwidth, we have to see now. Please observe here. Just observe CF, because the danger capacitor is only CF. The danger capacitor is only CF, is it not? So what is this CF experiencing? This I am calling it as V1 and V2. Or if you don't like this, we will draw AC equivalent like this. Here I am having Vin. Collector is connected to emitter, and base is grounded, and collector is connected to RC. Of course, this is a good view of a CB amplifier. This is CE connected to CB. A CE connected to CB, cascaded to CB, is called cascode. It's called cascode. Now, where is this Miller capacitance? The Miller capacitance is connected here. Let me change the color of my pen. This pen here. Yeah, this is my CF. Now, what was the Miller capacitance multiplication previously? It was CF multiplied by 1 plus GM into RC. Let me see what is V1 and V2 gain now. V2. So calculation of gain. Calculation of gain. So this transistor V1 is here. V2, the load for CE, please understand, the load for CE is the input resistance of the common base amplifier. In cascading, the load for CE is the input resistance. What is the input resistance seen here, R in here? It is alpha by GM. It is alpha by GM. So here you are having alpha by GM as your RC, and your capacitance is connected here, CF. This is V2. Now, what is V2 by V1? V2 by V1 is minus GMRC generally, but now it is alpha by GM. So GM cancel alpha. This alpha we can treat it as 1, right? Alpha is 0.99. We can make it as 1. So when your V2 by V1 is minus 1, what is the input capacitance here? Cin. Cin is going to be CF into 1 minus V2 by V1. So your minus V2 by V1 is 1. So it is 2 CF. So what can we write here? The Miller capacitance multiplication. What is this? Image has come. Why did this come? Okay, I'll make a note here. The Miller capacitance multiplication has decreased from C multiplied by 1 plus GMRC to 2C. 2C. So now the gain GMRC has become just 1, right? Or minus 1. It is 2C. So therefore, tau decreases, and bandwidth is improved. The Miller capacitance multiplication has increased from, what is this? Oh my God. How can I remove this? Any suggestions? Why did this come? Is there an undo option here? Oh, okay. Okay, no problem. I'll take a new flip book. So what are the three advantages of having a cascode amplifier? One is there is no change in gain. There is increase in bandwidth because of the Miller capacitance multiplication. And the Miller capacitance multiplication has decreased from C multiplied by 1 plus GMRC to 2C, right? And the third one is the output resistance has also increased. So there is no early effect. Whenever output resistance increases, such circuits don't have early effect, right? Okay. Now frequency response. Of common source amplifier. Common source amplifier. So I have a simple common source amplifier here. Now for this common source amplifier, this is a MOSFET we have already seen. So you have gate here, source and drain. These are N plus regions and there is a P substrate. Now suppose in a VLSI course generally what they do is they include 4 capacitors. 2 capacitors we have already included. One is CGS and the other one is CGD. So CGS and CGD are nothing but your C pi and C mu. They are nothing but your CGS and CGD. Your C pi and C mu. But between N plus and P, you can have one more if you want, right? So this is CS, the substrate is generally called bulk, CSB and CDB. So now you can include 4 capacitors in a MOSFET, right? So this one is CGS, this is CGD, and 2 capacitors from here to bulk, right? CDB and CSB. So 4 capacitors you can include if you want, but out of which one is this one, there's already ground here. So what happens when you connect a capacitor across the ground node? Across the ground node, CSB, this is neglected. And you have this capacitor, CDB, bulk, right? So 3 capacitors out of 4, one is missing, 3 capacitors are there. Now you tell me what is the bandwidth of this amplifier? What is the bandwidth of this amplifier? So you have to calculate the time constants, right? So here you have RS. Here there is a CGS. And here you are going to have Miller capacitance. This is CGD multiplied by 1 plus GMRD. At the input side, this is tau 1. At the output side, tau 2, what are the capacitors here? Here you are going to have R0, and then there is RD, and then you have a capacitor here, CDB, plus this capacitor, CGD. So let me draw it like this. C, this is gate and drain, CGD multiplied by 1 plus GMRD. And here you already have CGS is RS. And here you already have CGD multiplied by 1 plus 1 by GMRD. So this is very, very small, so you can neglect. And of course, one bulk, CDB bulk. So this is tau 1 and you have tau 2. So how many poles are there? 2 pole system, right? So what is tau 1? It is RS into CGS plus CGD, CGS plus CGD into 1 plus GMRD. And what is tau 2? Tau 2 here you have R0 also. R0 parallel with RC or RD into CGD, this is approximately CGD plus CDB. Oh, I hate this CGS, CGD. We'll make it C1, C2, that is better. Huh? So what is omega tau? This is tau 1, right? So what is the bandwidth of common source amplifier? It is 1 by tau. And what is tau? It is tau 1 plus tau 2. It is tau 1 plus. So you can just add them, then you will get bandwidth. If you want in hertz, then you have to multiply the denominator by 2 pi, 1 by 2 pi tau, right? So this is the common source amplifier bandwidth, the frequency response of common source amplifier. By including 4 capacitors, right? 2 capacitors extra I have included between the N and P. This is called the bulk, the source and the bulk, and the drain and the bulk. So 4 capacitors are there, right? Out of which one is missing because the source is already grounded. So it is like you have bypassed that capacitor, CSB. The CSB capacitor is bypassed. Is bypassed, right? So this is the frequency response of a common source amplifier. Similarly, you can find for other configurations also. Frequency response of what are the other configurations? You can have common source is there, common gate amplifier. Common gate does not have Miller effect, is it not? Common base does not have Miller effect. So why it does not have Miller effect? Because the terminal here is grounded. So where are the Miller capacitances? Here you are going to have CGS. This is CGD. And 2 capacitors from here to ground. One is from here to bulk, right? This is ground, CDB, and CSB. Am I right? CSB. Or if you don't like drawing like this, we'll draw it like this. Some students like common base like this, right? Like this. So you can draw like this. And here you can have what you call RS. And VS is shorted RS. And all of you, from this node to ground, you have CSB. From the same node to ground, you have CGS. So how is CSB and CGS? How is CSB and CGS? From the same emitter terminal or the source terminal, you have CGS and CSB. So they are in parallel, right? Similarly, observe this point here. From this node to ground, you have CDB. And from the same node to ground, you have CDB. CDB and what do we call this? CGD. CG. Oh, I thought to have C1, C2, I forgot. I'm stuck with all the CGS, CGD like that. So we have 4 capacitors here. So here there is tau 1 and here there is tau 2. So what is bandwidth? Bandwidth is 1 by tau. Tau is tau 1 plus tau 2. So what is tau 1? Tau 1 is Rs. What is the resistance seen through the emitter terminal or the source terminal? Gm. 1 by Gm. Rs parallel with 1 by Gm into CGS plus CSB. See, if two capacitors are in parallel, what is the overall capacitance? It is addition, right? It is addition. So what is tau 2? Tau 2 is going to be CDB plus CGD. It is going to be CGD into RD. But if you say that, no, sir, I still want this one also, right? So from here, can you tell me what is the resistance from here? Parallel with this guy, down, R0 plus 1 plus Gm R0 into Rs. Such a big value, parallel with RD is the same value. Are you getting? So that is why this one is a better diagram. Otherwise, you have to see like this, right? Like this. Okay, so it's RD parallel with R0 plus 1 plus Gm R0 into Rs. So this is tau 1 and tau 2. What is bandwidth? Bandwidth is simply 1 by tau. And tau is tau 1 plus tau 2. Tau 1 plus tau 2. So this is in radians per second. If you want in hertz, what you have to do? The denominator you have to multiply by 2 pi. Right? 1 by 2 pi RC. Right? So this is the frequency response of common gate amplifier. So like this, you can include a lot of capacitors like that. Because yesterday a student was asking in the doubt session, sir, how these capacitors are calculated? Once at that particular node, all the capacitors are being summed up, right? By the VLSI tool. We don't do it. The tool will add all the Miller capacitors and all the capacitors that are connected to ground, and it is going to give you an approximate delay offered by the circuit. So this is the frequency response of a common source amplifier, and this is the frequency response of common source, and this is the frequency response of the common gate amplifier. A common gate amplifier, right? So like that you can do it. What is the frequency response of cascode? Frequency response of cascode. Cascode. Oh, this time I'm taking C1, C2, okay? I can't have the CGS, CGD like that. So we'll have a so the lower one is going to be common source, upper one is common gate. A common source amplifier given to common gate amplifier is called the what you call cascode. Now please tell me, this one I'm calling it as C1. Is it okay, right? What is C1? You know it. What is C1? It is CGS. I'll call it C2. And this one is not there. I'll call it C3. This guy C4, C5. You have two here, C6 and C7. C7, okay? So how many nodes are there to calculate? One is a gate here. Next, this one and this one. 3 time constants are there. If you have a 2-stage amplifier, I told you in my first introduction class, if you have a single stage amplifier, you have 2 time constant, input time constant, output time constant. The order of the system is 2. If you have 2-stage amplifier, then you have 3 time constants. If there is 3-stage amplifier, you have 4 time constants. If there are 4-stage amplifier, 1, 2, 3, 4, 5 time constants. If there are n-stage amplifier, you're going to have n plus 1 time constant. It's going to be n plus 1 time constant. So, and what is C2 here? Be careful with C2. This C2 at the input side is going to be what? Miller. What is C2? C2 multiplied by 1 plus 1. 1 plus 1. That is going to be 2C2, right? So input side 2C2, output side also 2C2. Let me make it simple here. So here we are going to have RS. This is C1. The Miller capacitance is 2C2. How did you get it? C2 into 1 plus GM into 1 by GM. GM into 1 by GM. So it is going to be 2C2. 2C2. Input side as well as output side. If the gain is 1, output side also it is going to be C multiplied by 1 plus 1 by GM by 1 by GM. So that is going to be again 2C2 here. This is 2C2. Please tell me how many capacitors are in parallel at this node? At this node, how many capacitors? C3 is there, C6 is there, C4 is there. This is going to be C3 plus C6 plus C4. All right? At this point, right? At which terminal here? And then this guy, C6, C3 plus C6 plus C4. What about this fellow? Here, RD. At this point, how many capacitors are in parallel? C7 plus C5. They're going to be C. Let me count. Total 7 are there. So 1, 2, 3, 4, 5, 6, 7. And the Miller capacitance at inputs, output side is also C2. At output side also it is C2. So what is C output and C input for this Miller capacitor? C in is going to be C multiplied by 1 minus of minus 1. And for output side, it is going to be C multiplied by 1 minus of minus 1 by 1. So what is 1 or 1 by 1? 1 or 1 by 1 is going to be 1 only, right? So it is going to be 2C2 at input and 2C2 at output for the Miller capacitor. Okay, so now we are going to have 3 time constants, tau 1. This is tau 2 and here tau 3. Okay. So tell me what is tau 1 for a cascode amplifier. Tau 1, it is going to be RS into C1 plus 2C2. C1 plus 2C2. What is tau 2? Tau 2. What is the resistance here? It is 1 by GM. 1 by GM parallel with R0. Tau 2, 1 by GM parallel with R0 into how many capacitors are there at this node? 2C2 plus C3 plus C6 plus C4. 2C2 plus C3 plus C4 plus C6. And what is tau 3? Tau 3 is going to be, oh, there's a big R0 here. R0 plus 1 plus GM R0 into like that, right? And then this RD, right? So if you treat this as M1 and M2, this is going to be what value? RD parallel with R02 plus 1 plus GM2 R02 into R01. This is very large. Large parallel with small is small. And there you have a C7 plus C5. C7 plus C5. Okay, so what is bandwidth? It is going to be 1 by tau. And what is tau? Tau 1 plus tau 2 plus tau 3. So this is the bandwidth of a two-stage amplifier without the high frequency model. We didn't withdraw any high frequency model. And we included even the capacitors, the bulk capacitors, right? So 8 capacitors we included. So one is the source terminal is already grounded. So one is missing there, right? Now, why the cascode amplifier bandwidth is improved, though you have so many capacitors? See, simple, the GMRD value or GMR0 value is suppose, if it is R0, it will be like 1000. Say the gain is 1000. So you are multiplying 1 plus 1000, so it is 1001. So it's like simulating 1001 capacitors. But even though you cascade two stages, you are having hardly 7 capacitors, right? Out of which one is missing. But if it is multiplied by 1 plus GMRD, it is like 1001 capacitors. So if capacitors are more, tau will be more. If tau is more, bandwidth is going to suffer. So definitely, this is a wide band structure. This is what structure? A wide band. Like that, for any configuration, you can take the capacitors and calculate the time constant. So here you had this C2, and the C2 became 2 C2 at input and 2 C2 at output. Calculate the 3 dB cutoff frequency. Calculate the 3 dB cutoff frequency. Calculate the 3 dB cutoff frequency. Okay. So how do we solve this? Voltage sources should be short. So when you short it here, tau 1 is going to be R1 C1. Tau 1 is going to be R1 C1. This is tau 1. Here you can find tau 2. What is tau 2? Tau 2 is R2 C2. So what is total tau? Total tau is going to be tau 1 plus tau 2. It is R1 C1 plus R2 C2. So what is omega 3 dB? It is 1 by tau. 1 by tau. What is F3 dB? It is 1 by 2 pi tau. So it is 1 by 2 pi into R1 C1 plus R2 C2. So all our amplifiers are low pass filters, is it not? Low pass filters. If you neglect the lower cutoff frequency, then it is going to be low pass only. So here you are going to have omega 3 dB. What this calculation will tell you, this calculation tells you that whenever your input frequency is changing, whenever you are changing the input frequency, here frequency, this input frequency omega, this is omega, right? This is omega. That omega value should be less than, should be always be less than your omega in, should be less than omega 3 dB. What happens if your sine wave of your input is more than omega 3 dB? What happens if your sine wave of input is more than omega 3 dB? If this input is more than omega 3 dB, then this is gain. So your input here, this should be your omega in. Omega in. Your omega in should always be less than omega 3 dB. This is your omega 3 dB. So what happens if your omega in is greater than omega 3 dB? Then the gain is going to fall. The gain is going to fall. That is why we have to calculate the cutoff. They say it's a cutoff. It's like cutoff marks, right? You go for a GATE exam, there is a cutoff marks. But the only difference is the cutoff marks there is like high pass filter. Beyond that cutoff marks, whoever gets, they have passed. Rest else below the cutoff mark, somebody who gets, they are failed. But here, this is low pass filter. Low pass filter means it will set up a cutoff. Your marks, your input frequency should be less than the cutoff frequency. So the sine wave, what is frequency? The number of waves per second should be less than omega 3 dB or F3 dB. Then it will amplify. If you give anything more than that, then naturally signal will fall, right? But if you say that, sir, how did you get this? In my first class, I told you, whenever you have shunt capacitor, then it will have a transfer function K by 1 plus S tau. K by 1 plus S tau. It is a low pass filter. It is what filter? Low pass. So all our amplifiers are low pass filters. I have repeatedly told this in my first class. Are you getting? So all our amplifiers are low pass filters, and this is the last calculation in amplifiers. If you remember, I told you the first calculation in amplifier is strength, gain, voltage gain, current gain, power gain. The second calculation is its impedance matching, Rin and R0. The third calculation, the last calculation, is the frequency reach of the amplifier, which is the bandwidth. And bandwidth calculation is very, very easy. You have to calculate tau, then add the tau, and bandwidth is 1 by tau. Bandwidth is simply 1 by tau, right? Yeah. Now the bandwidth calculation is little crucial because you have an extra Miller capacitor coming into picture. Miller capacitor. So whenever there is a capacitor here, what you will do? You will split that capacitor into two capacitances by first naming the nodes here. This is V1 and this is V2. V1 and V2. So how will you solve this? To solve this, okay, we'll short the voltage source here. Let this be R1. Here you are going to have C1 already, C1. And this is Vin. Here there is GM Vin and C2 R2. R2. Am I right? Now you're going to have two capacitors. What shall we call this? This capacitor here? We'll call it Cx and we'll call this as Cy. Am I right? Cx and Cy. What is the value of Cx? Right? Cx and Cy we will see. What is tau 1 and what is tau 2? Tell me what is tau 1? Tau 1 equal to R1 into C1 plus Cx. What is tau 2? Tau 2 is going to be R2 into C2 plus Cy. C2 plus Cy. C2 plus Cy. Now what is this Cx and Cy? We should know the gain of the amplifier. So for calculating gain, all the capacitors should be open circuits. Capacitors open circuit. Then here you are having Vin. This is GM Vin. And here there is R2. Right? Now where is V1 and V2? See here, V1 is nothing but Vin. V1 is nothing but Vin. V1. This is V1. Where is V2? Where is V2? V2 is at this current source here, V2, right? So what is V1? V1 is Vin. What is V2? If this current is minus GM Vin into R2. So what is V2 by V1? It is minus GM R2. V2 by V1 is minus GM R2. Then what is Cx? It is C3 multiplied by 1 minus V2 by V1. It is going to be C3 into 1 plus GMR2. And what is Cy? Cy is going to be C3 into 1 plus 1 by GMR2. So this you can substitute here. Therefore, tau 1 is R1 into C1 plus C3 into 1 plus GMR2. Tau 2 is R2 into C2 plus approximately C3. This value is very small. Total tau is tau 1 plus tau 2. Bandwidth is 1 by tau. Bandwidth is 1 by tau. Okay, so who suffers with Miller effect here? Only C2. Only C2. And what is the value of that? What is the value of Miller capacitance? The Miller capacitance is multiplied by C multiplied by C2. C2 multiplied by 1 plus GM into 1 by GM. What is the input resistance of this amplifier? The input resistance of this amplifier is going to be 1 by GM, which is the load for this stage. So that is something we have done here. Am I right? For the previous case. So what are the parallel capacitors here at T2? C3, C6 and C4. C3, C6 and C4. From here to ground, from here to ground, from here to ground. What are the capacitors here? From here to ground, C5, C7. What are the capacitors from here to ground? Only C1, but the reflection of C2 will be there, right? 2C2. Okay, shall we take a break? Right? We'll take a break. When we come back, we will see more of this. Okay. Can you hear me?
Yes, sir, audible.
Yeah, thank you. Find V naught by Vs. Find V naught by Vs. Okay. Now find V naught by Vs. This is the mid-frequency gain. Mid-frequency gain. That means this is just the AC analysis we have to do. AC analysis, right? Only when the examiner says calculate cutoff frequency, then what you have to do? You have to remove that capacitor, open circuit, and calculate the R Thevenin or R equivalent, and tau is going to be R equivalent into that capacitor. Are you getting? But don't forget our AC analysis, mid-frequency analysis. All the capacitors are treated as short circuits, and DC sources for AC analysis, what should we do to voltage sources? Short circuit. Current sources, open circuit. Capacitors, short circuit. This is for AC analysis. Are you getting? When you are calculating gain. But if a capacitor is given, he's asking you to calculate the cutoff frequency, then what you have to do, that capacitor you have to open circuit and calculate R equivalent. What happens if you short that capacitor? Then tau will be equal to R into C. C is short. If C is short, there is 0, right? There is no tau at all. Are you getting? Easy. There your aim is to calculate the time constant. So open circuit the capacitor, calculate R Thevenin or R equivalent. Tau is equal to R equivalent into C. Okay. This is general mid-frequency analysis we have already done. Now, if capacitor is treated as short circuit here, this is ground. Am I right? This is ground because capacitor is short. Now you can see here the RF is connected to ground. So I can draw RF here also, because from here to ground it is connected, and this RL comes in parallel. The RL is here. So this is no Miller capacitor. This is no Miller capacitor. Miller effect is seen only when one of the terminal is, if one of the terminal is grounded, then there is no Miller effect, right? So this is a normal RF capacitor which is across RL, right? So now, or you can draw like this. So this is a simple common base amplifier where you have RF parallel with RL. So tell me, what is V0 by V? Common base will not give any phase shift. Am I right? So numerator IC, denominator IC. So your V0 is going to be RF parallel with RL by, in this Vin, wherever VGS is there, or VB, 1 by GM here, plus what should I do to emitter resistors for voltage gain? All the emitter resistors are divided by alpha, base resistances are divided by beta. So it is RS by alpha. It's RS by alpha. So this is the voltage gain. This is the voltage gain of the amplifier, 1 by GM plus RS by alpha, RF parallel with R1. So remember, in voltage gain, emitter resistors are divided by alpha, base resistances are divided by beta. If you still have an element of doubt, then one Kirchhoff's law you can write. Here IC, here IE is there, here VB is there. So what is V0? V0 is minus ICRC. V0 is minus ICRC. VS equal to minus of VB plus IE into RS. Then numerator you can have IC here, and denominator you can have IC, and then cancel them. You will get RF parallel with R1 by 1 by GM plus RS by alpha, right? So in this problem, you can take, because this is a previous paper problem, the examiner has given VA infinite. All our previous paper questions, VA is what? Infinite. Early effect is infinite, right? Now what about this? This might look like a Miller resistor, am I right? Here we have VS. Now there is RF here. Now this RF, we are going to split it into two resistors. What are they? One is RF by 1 minus V2 by V1. And this one is approximately RF. Right? Now, if you draw a Thevenin equivalent for the input, you realize that this resistor has no meaning. A resistor in parallel to a voltage source has no meaning. It's the same voltage, right? So there is no meaning in calculating V2 by V1 also. It's waste of time, right? But if you have a series resistance, then okay. But here directly Vin is there. a resistor in parallel to a voltage source or a resistor in series to a current source. Both have no meaning, right? So what can we do? We can just remove it, or you can replace it by Thevenin equivalent. You will have only voltage. The resistor is missing, right? There's no resistor there. Yeah, it might affect the input resistance. It might affect the input resistance, but voltage it cannot change. Voltage it is never going to change. So this is RE here. And here you are having RF parallel with RL. And this is going to be your Vin. And V0 is here. So what is V0 by Vs? Or Vs, right? V0 by Vs. So this is like a common emitter amplifier. So we should put a negative sign. So what you'll write in the numerator? IC into RF parallel with R1. In the denominator, what you can write? This drop plus this drop. So RE by alpha, because emitter current is flowing. And VB is nothing but 1 by GM into IC. So this is going to be the gain of the amplifier. Now, if you have an RF here, and R1 here, then how do you find V0 by Vs? How do you find V0 by Vs? Va is infinite. You can take some values, beta and all that, right? Beta 100, Va infinite, like that. Now you have to consider Miller effect. Now you have to consider Miller effect. In the previous case, Miller effect we will consider, but it is waste of time because this resistor is directly coming in parallel with a voltage source. A resistor in parallel to a voltage source has no meaning, right? Okay, so how do we solve this? So many ways of solving, right? And what is the first procedure we have followed in AC analysis? Before going for AC, we can do what analysis? DC analysis first and calculate the current, and then you can go for AC analysis, right? So some values are given in exam. There's something like 3K, 10K, 1K, like that. Some supply voltage is given. So first DC analysis, capacitors are replaced with open circuit. Open circuit. V or VCC, whatever, you can call it VCC. Now, whenever you are doing DC analysis, don't forget you have to take how many volts here? 0.7. Examiner will give you. This is IC. This is IC. This current is IB. And what is the total current here? It is IC plus IB. The total current is going to be IC plus IB. Now you can apply KVL in this loop. KVL. So this is VCC with respect to ground. VCC. So you can apply KVL, right, in this loop. Minus VCC plus IC plus IB into RC plus IB into RF plus 0.7 equal to 0. Right? And then the second equation is how to eliminate IB. IB equal to what will you get? IC by beta. IB equal to IC by beta. Substitute 2 in 1. You get IC. Substitute 2 in 1. You are going to get what? IC. Once you get IC, what is GM? It is IC by beta. And what is R pi? It is beta by GM. So this is DC analysis. This is DC analysis. You will get these values. Am I right? After getting all these values, IC, GM, and beta, then you can have the small signal model. Small signal model. What is the small signal model of BJT? If there is no early effect, you can have R pi, GM V pi, or beta IB, your wish. Beta IB. So this is the small signal model. Base, emitter, collector. Right. So think how we can do by shortcut also. First by normal procedure, otherwise normal procedure you will forget, right? So now we can go for AC analysis. In AC analysis, we have R pi here, beta IB. This is base, emitter, collector. Now you have to make connections. What are the connections here? If you short circuit, what is AC equivalent? AC equivalent. Capacitors are replaced by short circuits, right? So you have BJT here, RF, RC, R1. This is AC equivalent, am I right? So this we have to connect. From collector to ground, you have RC, where you take the output. From base to ground, there is R1 and V. Base to collector, there is RF. Here, RF. Emitter is grounded. So it's a simple network. If you solve this, there is no need of, suppose somebody says, sir, I don't remember Miller theorem. No problem. You can solve by this method, right? So what is IB here? Okay, there is one unknown node, V0, Vin. We don't know this node. We'll call this node as VB. Shall we call it VB or VX? Some VX we'll take. So this is going to be beta. IB is nothing but what? Vx by R pi. Vx by R pi. So there's only one unknown node. If you apply KCL, entering current equal to leaving, you can solve. So tell me KCL at this node. KCL. This node is V naught. V naught minus Vx by Rf plus beta into Vx by R pi plus this is the current plus V naught by Rc equal to 0. So sum of currents that leave a junction is 0, right? This is V naught. V naught minus Vx by Rf plus beta Vx by R pi plus V naught by Rc equal to 0. In the second equation, sum of the currents that leave a junction is 0. Vx minus Vin by R1 plus Vx by R pi plus Vx minus V naught by Rf equal to 0. Now from 1 and 2, what you can do? You can eliminate Vx, and just take Vx common here, Vx common, you will get some equation. If you eliminate Vx, then you will get V naught by Vs. So this is a simple, what you call KCL. There is no need of Miller theorem, right? Miller is just an approximation. You will get an exact answer in this, right? But what does the examiner want? The examiner wants an approximation, right? Just by seeing the circuit, you have to tell the answer for 2 marks. For 2 marks, we cannot do all this, is it not? Yes, we can do. If the same problem is given in IES exam for 10 marks, then we can do one DC analysis you can do, and after that you can go for AC analysis. I mean, if there is no other way out, then we have to do, is it not? You have to spend 2-3 minutes and you have to do it if you don't know another way of solving it, right? Method 2 says that now the second method says that you can do by Miller also, right? So what is Miller's theorem here? Here you have a RC, R1 is Vs, and here there is Rf. Am I right? This is V naught. So now, as usual, this is V2. V2 and V naught are same. This is V1. Now we have to split it into 2 resistors, right? As a Miller approximation. This is going to be Rf divided by 1 minus V2 by V1. This is approximately Rf. This is approximately Rf, right? Now, what is V naught by Vs? V naught by Vs is going to be, V naught is nothing but V2. V2 by Vs. Am I right? So it is going to be V2 by V1 into V1 by Vs. V2 by V1 into V1 by Vs, right? So V2 by V1, which is a gain, of the amplifier. And what is V1 by Vs? What is V1 by Vs here? V2 by V1, V1 by Vs. So I told you V1 by Vs, you have a Rf by 1 minus V2 by V1. And then there is an R pi here. R pi is V1. And you have R1 here. and there is Vs. Vs. So what is V1 by Vs? V1 by Vs is Rf by 1 minus V2 by V1 in parallel with R pi by Rf by 1 minus V2 by V1 in parallel with R pi plus R1. Something we got. Okay. Just tell me, what is a small resistance parallel with a large resistance? This is important, right? Small r parallel with large r is equal to small r. Small r plus large r equal to large r, right? So V2 by V1 into small parallel with large is small, Rf by 1 minus V2 by V1. And small plus large is large, R1. What is 1 minus of large value? Large value. 1 minus large equal to minus large. 1 is neglected. So, your V0 by Vs is going to be V2 by V1 into Rf by minus V2 by V1 by R1. So V2 by V1 cancel, minus Rf by R1 we got. So the gain is very, very simple. It's minus Rf by R1 as a best approximation. That is something method 3, we will study method 3 in the feedback amplifier section. In feedback amplifiers, if you have an RC here, and if you have beta or A, whatever, right, A very large, and here if you have RF, and here there is an R1 here, then what is the gain of such an amplifier? The gain of such an amplifier. The complete forward path is getting desensitized. The gain will depend only on the resistor. So your V0 by Vs is simply minus Rf by R1, minus Rf by R1. So the examiner is asking for 2 marks. How will you solve? And nicely he will give beta, whatever you want he will give. Now you should not get tempted by looking at beta 100, VT 25 millivolt, this, that. If you start doing DC analysis, AC analysis, DC analysis, AC analysis, then ultimately you are going to waste time. You are going to waste time, right? So anytime you find an amplifier like this with an R1 and RF, don't forget that this V0 by Vs is simply minus Rf by R1. Minus Rf by R1 is the gain. If you say, sir, I don't believe this because you're comparing with op-amp, then I have proved using Miller's theorem, right? Using Miller's, if you want a proper answer, you have to stop here. But I made few approximations here because in gate problems, he's asking what is the approximate. I think 2 times he has asked in gate. If I remember, once he has given 10K, 1K. Then he has given 53K and 5.3K, something like that, right? But answer is what? 10K, 1K. Your answer is minus 10. 4 options are there. Minus 10, minus 100, minus 50, like that. Minus 10 is the right answer. But if you do first DC analysis and then AC analysis, which I have done, the answer was coming 9.78 something, right? So 9.78 after so much of labor. And then finally you'll think, okay, the answer is close to 10. But that is a wrong approach. The right approach is, in analog, you should not do anything, right? A good analog engineer should not do anything. But just by saying, you should tell the answer, right? But how would you arrive at that answer means DC analysis, AC analysis, we have to do initially, right? Initially, we will learn like this. So slowly, we will build an intuition. And finally, we'll come to that conclusion here, right? So it's V2 by V1 into small resistance parallel with large resistance is small by small plus large is large. And 1 minus large is minus large. So 9.78 with all that other masala, you're going to get 9.78. But now we have got minus Rf by R1. Minus Rf by R1 is the gain of the amplifier. Just by looking at the amplifier, If this is 10K, this is 1K. Suppose this is 10K, 1K, 1K here. Then your answer is going to be minus 10. Your answer is going to be minus 10. Are you getting? 1 minus 100 is minus 100. Minus 99, like minus 100. 1 minus 100. Method 1 you should try. Always method 1. That is how you cross check. See, for gain calculation, because this is approximation, Miller's approximation, if you want accurate result, for gain calculation, it is better you include this RF also at output, because its reflection is seen here. If you want to gain calculation, then the gain is going to be minus GM into RF parallel with RC. See, these are the limitations of having Miller's theorem. That is why, remember, Miller's theorem is not for resistors. Miller's approximation is for capacitors. With resistors, we can do like this method also. Yes or no? This method will give you 100% accurate answer. Here, right? Pakka with decimals you will get. If you want an approximation, you can go for Miller, but then again you are calculating the gain. When you are putting an effort to calculate the gain, you can as well calculate here also, right? But the best one of all this is by inspection. The V0 by Vs is minus Rf by R1 minus Rf by R1. Okay, so this is about the frequency response, and we have seen all the combinations like common collector with common collector with common emitter, common collector with common base, common emitter with common base, common emitter with common emitter, and multiple stages, 3 stages also we have seen. The last one missing is the Darlington pair. The Darlington pair. Advantages: high current gain, high input resistance. High current gain, high input resistance. Because of huge current, the application is it is used for or used as a power booster. So most of the power amplifiers, last stage will have the power boosting, the Darlington pair. But how does this Darlington pair look like? Something like this. It is used as a power booster, as Okay. So what is the relation between IE and IX? IE and IX. IX happens to be the base current, right? IX happens to be the base current. So what is IE and IX? IE is beta plus 1 times of IX. Am I right? But what is the relation between IX and IB? IX and IB. IX happens to be the emitter current and IB is a base current. So IX can also be written as beta plus 1 times of IB. So finally, what is IE? It is beta plus 1 whole square times of IB. Tremendous current gain. High current gain. IE is beta plus 1 whole square times of IB. Right? So what is the relationship between emitter current and the base current? Emitter current, always IE is always equal to IC plus IB. IE is IC plus IB. IC is beta IB plus IB. So your IE is beta plus 1 times of IB. Are you getting? Right. So emitter current is always beta plus 1 times of the base current. Why? Because emitter current is collector current plus base current in any BJT, right? High current gain. What is the input resistance of a Darlington pair? Suppose this is a Darlington pair. And here you have RE. How do you calculate the input resistance RN? RN. First, you have to calculate RX. All right. What is RX? RX is going to be, you are seeing through base terminal. It is R pi 2 plus 1 plus beta times of R. It is R pi 2 plus 1 plus beta times of R. So, the Q1 transistor has Rx now. Rx. So, what is Rin? Rin is going to be R pi 1. Right? This is Rin. Rin is going to be R pi 1 plus 1 plus beta times of Rx. It is R pi 1 plus 1 plus beta times of Rx is nothing but R pi 2 plus 1 plus beta times of R. So this calculation of input resistance is given for 10 marks in IES exam, right? So by intuition, you can directly do it because 10 marks is there, do some time pass, draw the small signal model, do some time pass and finally write this answer, right? R pi 1 plus 1 plus beta times of R pi 2 plus 1 plus beta whole square times of R. This is your R. Now, in the IES exam, the RE was given 8K, and beta is around 100, right? So what is 100 square? 100 square is 10,000 into 8K. So that means Rin is approximately 80 mega ohm. 80 mega ohm. So this is the calculation of input resistance Rin. Calculation of input resistance Rin. 80 mega ohm, right? Huge, very, very large input resistance. So two advantages of Darlington pair. Two advantages of Darlington pair, right? One is the input resistance is very high, and the second one is what? It has tremendous current gain, right? Tremendous current gain. See, what do you mean by large current? There are two ways of looking at it. What do you mean by large current? What do you mean by IE equal to beta plus 1 whole square into IB? In my opinion, I like somebody writing an equation like this. IB equal to IE by beta plus 1 square. So what do you mean by that? You might say IE is very large, but I would prefer saying that your IB is very small. right? The base current of such a pair is very extremely small. That is why with a small current it can drive. It can drive. For example, yeah, I remember students when they are doing project, right? So they wanted to drive a robot. So one of the student used a normal regulator, something like 7809, 7805. This 7805, the 78 series maximum will give 1 ampere, 1 ampere. That fellow, he has put a load of a low value. This is 5 volt, low value. Suppose this load is like 1 ohm, 1 ohm. 5 by 1, how much current will flow? 5 ampere. But maximum current this fellow will give is only 1 ampere. So finished, gone. The IC is gone, right? Or some students use IC, what is that variable regulator? IC 723. This fellow will give maximum only 100 milliamp. More than that he can, but you want to drive a robot. What you will do? 100 milliamp. This 100 milliamp, first we will give it to a BJT. Here we will connect the resistor RL. But yes, you will lose 0.7. So here, this voltage we will vary to 5.7. 5.7. So you are going to get 5. Now, if you connect in a common collector fashion, what will happen? This current 5 by this RL is going to be 5 ampere. 5 ampere. If suppose if your beta is 10, 5 ampere by 10 will be the base current. 5 ampere by 10 is the base current. That is going to be around 500 milliamp. Am I right? 500 milliamp. Now, IC 723 can give only 500 milliamp means what? Then what we have to do? We have to replace this with a Darlington pair. You have to replace small current is there, 100 milliamp. I am going to get a large current now. I'll put a Darlington pair here. And I need an extra 1.4 volt drop. 5 plus 1. I'll make it 6.4 here. So this is going to be 5 volt. This is 1 ohm. So naturally the current is 5 ampere. So when this is 5 ampere, this is going to be 5 ampere divided by 1 plus beta whole square. This current is less than 100 mil. This current is less than 100. 5 ampere by 100. Are you getting? Less. If still current you want, if suppose you say no sir, yesterday I was using IC 723, now I'm using a new IC. That IC will give only 5 milliamp. What should I do? No problem. Put a Darlington pair here. Darlington. Darlington means 3 transistors. Please, Darlington is a name of a person. Darlington is not a name of a person. Darlington means a fancy way of saying 3 transistors. Darlington was working for Bell Labs. This man working for Bell Labs. And the good news is he has got nothing to do with circuits. He is basically a theoretician. He used to write some theory, right? He was working for Bell Labs. But he wants to tinker with circuits and there is no opportunity for him because he is a theoretician. He has to write only theory there at Bell Labs. So one day, Darlington took 2 transistors home over a weekend. I think you also would have done that, is it not? In your lab, what you will do whenever you find transistor, slowly you will take and put in your pocket. Yes or no? Nobody sees, the lab assistant does not see. So this Darlington has done that. 2 transistors he took, put in the pocket and he left home. At home, he connected the transistors in this fashion. And when he connected it, he has let out 3 terminals for it. 3 terminals, see? 3 terminals only. Beautifully as connected. This is the base of the composite pair. This is the emitter of the composite pair. This is a correct collector of the composite pair. Now, why did he did this connection is, when transistors were invented, at Bell Labs, there were very few transistors, but beta varied from 5 to 15, that's all. 5 to 15. Any transistor manufactured with between 5 to 15, it was so difficult for them to do experiments because with 5 gain, what you will do? Yes or no? So when Darlington, he took these 2 transistors home, he connected like this, he found that this is not beta. This is also a transistor, but with 3 terminals, but the gain is not beta, it is beta square. So next day when he came to office after the weekend, he went to the die making people. He said, boss, I have one circuit. You put it in a die and let out 3 terminals. Those 3 terminals, he went and tested. When he tested, he felt very happy because at home there was no testing. He just connected, he was thinking. When he tested, he felt very happy. The beta suddenly varied from, if it was 5, is almost more than 25. So now Bell Labs started claiming that we have transistors where beta varied from 25 to 225. Are you getting? Now they can claim that if you want to do any experiment with beta 100, I will give you. Are you getting? So they will take 2 transistors with beta 10, 10 like that and make it 100, 15, 15, 225. Is 15 square 225? Is my maths okay? Right? So now the beta variation is from 25 to 225. So slowly Bell Labs people have patented this. Yes or no? Very simple. One transistor is there. They were doing all sorts of experiments with a single BJT. And this man, Darlington, who has got nothing to do with circuits, nicely took home and then created a nice transistor, a composite transistor from the 2 transistors, right? Okay, so now you tell me, with Darlington pair, 2 ways of thinking. One is output current will be large. That is one way. Second way is your input current is extremely small. So if any IC has very small current but the output load needs large current, then in between you can put what pair? A Darlington pair. With small current you can drive and give a large current at the output. So 2 advantages. One is high current gain. The other one is the high input resistance. Okay, so this is all about BJT and MOSFET. The last topic in BJT and MOSFET is the current mirror. But before that, I want to tell you there's an elegant way to calculate voltage gain. An elegant way to calculate voltage gain. So from where we have got this idea is from a single transistor or a single MOSFET if you have. What is the MOSFET equivalent? The MOSFET equivalent is, if you want to find V0, Vin, then here you are going to be having GM V pi, and this is R0, and this is V0, and here we have V pi, which is Vin. All right. So what is V0 by Vin? V0 is going to be minus GM V pi into R0. Vin is V pi. So V0 by Vin is going to be minus GM into R0. This is from the Norton equivalent. This is from what equivalent? Norton equivalent. So what is GM? GM stands for the short circuit transconductance. Short circuit transconductance. And R0 stands for the output resistance. Output resistance. So this is something we know, is it not? Now, suppose in this box, now how do I know that there is a MOSFET here? What if I put 100 MOSFETs inside? If I put 100 MOSFETs inside, again you will short here and draw the Norton equivalent. No? Whether there is one MOSFET or two MOSFETs, if you short it, you will have a Norton equivalent. If you calculate R naught, that is output resistance. Then the gain is going to be minus of short circuit transconductance into output resistance. Yes or no? So what happens if I have many MOSFETs? How do I calculate the voltage gain? How to calculate? If I have many MOSFET, 10 MOSFET, 15 MOSFET like that. Then step 1, find the short circuit transconductance. I naught by V. So if you have many MOSFETs, you apply V in and you short here, and instead of ID, it is going to be I naught. So I naught by V in is the short circuit transconductor. Step 2. Again, you have many MOSFETs here. For this, calculate the output resistance. So this is like drawing the Norton equivalent for many MOSFETs at a single stretch, right? Otherwise, what we've been doing, this is for one MOSFET, 5 MOSFETs are there, 5 times you draw. The headache, no? 5 times why you have drawn. So you'll have to go back to basic. From where this we have got? We have got this because we shorted. We calculated GM. So if we short for 5 MOSFETs, then directly GM you will get, no? You will directly get GM here, which is GM, capital GM total. Calculate the output resistance. For output resistance, what will you do to voltage source? Short. Here you have to apply a test voltage VT. Find IT. So what is R naught? R naught is going to be VT by IT. If you do these two, or intuitively if you can find, then the last step is directly, what is the gain here? See here, this is the third step. What is the third step here? Your AV is going to be minus of the total transconductance into the output resistance. AV is going to be. So otherwise, one MOSFET, one small signal, again another small signal model, again another small signal model, again Kirchhoff's law. Then you start from where did you get this idea? Because for single MOSFET, I draw Norton equivalent. For single MOSFET, when you can draw Norton equivalent, for 5 MOSFET, can't you draw directly Norton equivalent and tell AV is minus GM R naught? Yes, sir? Right. So this is a nice way, because we are going back to the roots and thinking how all this has started. Because we have drawn Norton equivalent for one MOSFET. Why not extend it for many MOSFETs in a single stretch? Are you getting? Okay. Example 1. So how to find AV for this? Step 1. Step 1. This MOSFET, we have to short at the output. At the output port, we have to short. You can see here, this is the output port here. We have to make V0 0. I0 by V in when your V0 is 0. That is the short circuit transconductance. So you have to make V0 0 and you have to give ID here. This is V in or VGS. So what is GM? GM is going to be ID by VGS, ID by VGS or ID by V in. It is going to be the transconductance, right? Or I0. This is I0 in our. So I0 by, you can write I0 by V in. I0 by V in is your transconductor GM. Step 2. What is the output resistance of this? Output resistance R0. For calculating output resistance, we have to short RD here and R0 here. So your R0 is going to be RD parallel with R0. Then what is the last step? The step 3 says that AV is going to be minus of GM, which is this is the total GM. GM total. GM total is going to be I0 by V in. I0 by V in, which is minus GM into R out. It is minus of small gm into R0. R0 means RD parallel with R0. So it's already a single BJT, so you don't know its a benefit, right? It's just to tell you that we already know it is minus gm into RD parallel R0. Now, when you will know its benefit is, suppose if I give you a problem like this, where you have multiple MOS, multiple means 2, we can take 2, then we can make 5 or 10 or whatever, right? This is M1, M2. Now, if I give this problem, a student will suddenly will not know what to take at output because output current source is there. Are you getting input V in is there? So he does not know how to solve, right? At least at the first stretch, he might get confused. So step 1 says that don't get confused. Just inject a current. Inject a current. If you inject a current I0, then the same I0 is going to flow here, I0. And V in is nothing but VGS1. I0 is nothing but ID1. So what is the total GM? The total GM is I0 by V in is nothing but ID1 by VGS1. It is GM1. So upper transistor is not going to, of course, these two transistor is a gate question. This one is a gate question for 2 marks. The step 1 is a gate question for 2 marks. So the overall transconductance is going to be the lower transistor, not the upper one, right? It is nothing to do with ID2 and VGS2. It is something to do with ID1 and VGS1. So this is GM. Now what is step 2? Step 2 is the output resistance. Now tell me, what is output resistance here? Output resistance. It is R02 plus 1 plus GM2 R02 into R01. R01, that is going to be GM2 R02 R01. What is step 3? Step 3 says that AV is going to be minus GM into R0, which is minus GM1 into GM2 R01 R02. So this is a cascade amplifier. It's a cascade amplifier, but it is having an active load. This is an active load. If you have a cascade amplifier with a current source as the load, see how nice the equation we have got. GM1, GM2, R01, R02, GM1, GM2 into R01, R02. What is GM1 alone? GM1 is the short circuit transconductance of this amplifier. What is GM2, R01, R02? It is nothing but the output resistance of the amplifier. So a cascade amplifier is going to give you GM1, GM2 into R01 into R02. But if you have RD finished, the moment this current source is replaced with RD, the whole big resistance in parallel with RD is RD. So GMRD. So I mentioned in Cascode that the gain is still same because the common emitter gain and cascode amplifier gain both are same because there's an RD. Now what I'm saying, I can increase the gain also. Forget about bandwidth. Gain also we will increase. How to increase the gain? The passive load has to be replaced with what load? Active load. Then you imagine the gain bandwidth product. Bandwidth has already improved with Cascode. But if you increase the gain also, the gain is not minus GM into RD. It is GM1, GM2, R01, R02. Are you getting? So this is the one more way of calculating voltage gain. First, you have to do the short circuit transconductance and the output resistance also, right? So what is the short circuit transconductance for this? What is GM? Step 1. If you short, same current is going to flow. I told you whatever you write in the denominator, that is the short circuit transconductance, I naught by V in. So what you'll write, I naught by V in is going to be 1 by, tell me, in KVL, if you apply KVL at the input side, whatever you write for denominator, that is nothing but short circuit transconductance. So you'll write RS plus 1 by GM, no? Yes or no? What will you write? This is I naught. This current is also I naught. So what you are writing for V naught by V in, do you remember you are writing V naught by V in, and what you will write in the denominator for V in? This loop RS plus 1 by, this itself is the short circuit transconductance. It is the short circuit transconductance. So this is, or you can take this as ID by ID. ID. This is 1 by RS plus 1 by GM. Now step 2, what is the output resistance of such an amplifier R0? First you should know Rx. What is Rx? R01 plus 1 plus GM1 R01 into Rs. Am I right? Then what is R0? It is R02 plus 1 plus GM2 R02 into Rx. Now here you can substitute the value of Rx. And last step is AV. AV is minus GM into R out. GM is 1 by RS plus 1 by GM into R02 plus 1 plus GM to R02 into Rx. Rx you can substitute. See, in exam for 2 marks, what they are asking, they should actually ask the whole thing, no? They will not ask. They will ask only step 1 for 2 marks. I have seen so many gate papers. Complete voltage gain they will never ask. They'll say calculate the short circuit transfer. What is there to calculate? One current you will send, I by V you have to do. Are you getting? So if you see previous questions, they ask only the short circuit transfer, only first step, right? But if they ask 3, then it is good, but a little lengthy, is it not? The main aim of doing all this is to go for the 3rd step. But gate problems, only first step they will stop. Calculate these are gate problems. These are gate problems, the short circuit transconductance. I naught by V. I naught by V. And given what is GM1? It is IC1 by VB1. Or what is GM1 in MOSFET? ID1 by VGS1. What is GM2 if BJT? IC2 by VB2. In MOSFET, ID2 by VGS2. But he don't want ID1 by V. He wants I0 by V. So what do you mean by I0 by V? It is a transconductance of a multiple transistor box, right? The overall short circuit transconductance I0 by V you want. So how will you solve this? So transconductance means whatever you write in the denominator of the voltage gain. Whatever you write in the denominator of voltage gain, that is going to be the short circuit transconductance. For example, what will you write here? What is I0 by V? Calculate the short circuit transconductance. So whatever you write in the denominator for voltage gain, that is the short circuit transconductance. I don't know why examiner has given this. This one we have already done. So in this, 4 questions are previous gate. 4 twos are 8. For 8 marks, they are given 2 plus 2 plus 2 in different years, right? Short circuit transconductance. Okay. Yeah, tell me. We can take some intermediate point here, Vx. Vx. So what is I naught by V? The total GM is going to be I naught by V. Am I right? So how to do this? I naught by V. Can I write I naught by Vx into Vx by V? All right. So I naught is nothing but IC2. Vx is nothing but VB2. So it is IC2 by VB2 into Vx by V. What is Vx by V in here? Here you are going to have R pi 2, V in and Vx. So here it is R pi 2 and this is V in. So it's approximately R pi 2 by R pi 2 plus 1 by Gm or alpha by Gm. This is the gain, or R pi 2 by alpha, R pi 2 by alpha, like that you can. So this value is approximately 1. But what is IC2 by VB2? IC2 by VB2 is GM2. This is almost 1 because R pi 2 is much larger than alpha by Gm. So what is the total GM? The total GM is going to be GM2. GM2. Now what is the simple logic for this? Simple logic. The Q1 transistor is an emitter follower. It is what follower? Emitter follower. What do you mean by emitter follower? Your Vx is approximately V. Your Vx is approximately V. So like this also you can do, or I naught by V in is simply I naught is IC2 and V in is nothing but Vx. V in is nothing but Vx. Am I right? Because the output at emitter follows input. So what is IC2 by Vx or VB2? VB2, it is going to be GM2. So the total transconductance is decided by the Q2 transistor. It's decided because complete V in is here. This is also V in only. So this is also V. Are you getting? So the overall transconductance is going to be GM2. So what about this circuit? I naught, see if your I naught is your ID, here ID, and here again you have the ID here. So you can write 1 by GM1 plus. So even if there is a resistor here in the place of I naught, what will be the gain? The gain is going to be what value? GMRD by 2. So that GM by 2 is the transconductance. RD is nothing but the output resistance. Am I right? So how can you do this? This is I naught. You can call it Vx. So what is the solution now? The total GM is going to be I naught by Vx. I naught by Vx or I naught by V in. This is nothing but I naught by Vx into Vx by V. I naught by Vx is nothing but the transconductance of M2 transistor, M2, which is GM2. GM2. And what is Vx by V? Vx by V. This is V in. Here you are going to have 1 by Gm. So it is 1 by Gm2 by 1 by Gm1 plus 1 by Gm2. The examiner said both have the same transconductance. This value is almost 0.5, 0.5 Gm2. It is going to be 0.5 Gm2. 1 by Gm plus 1 by Gm we will write, no? Generally for the input loop. Whatever is there at the input loop, that is the transconductance I told you. So it's 0.5 Gm2. 0.5 Gm2. or you directly write input loop. What is there? What is the input loop for this? Tell me, what is the input loop for this? Huh? For V naught by V in, if there is a resistor V naught by V in, what is the input loop? We can write it here. I told you, if this current is IC and this current is also IC, all the emitter resistors should be divided by alpha, base resistance should be divided by beta, and then the BJT should be given 1 by GM. Do you remember this? Yes or no? So the overall transconductance GM total is, if you just remove what is there in the numerator and put 1 by, and whatever is there at the input loop, that is going to be your transconductance, right? Because if this is I naught, this is also I naught. So this is also one reason why I want numerator to be IC and denominator to be IC, because when you short and inject IC, whatever you write in the denominator, that becomes the transconductance. That becomes the transconductance of the BJT. So all the emitter resistors by alpha, base resistor, or you can do like this. I naught is IC by IC into this value. IC cancel. 1 by RE by alpha, RB by beta, plus 1 by G. This is your GM total. So anything that you imagine some load is there, and anything that you write in the denominator, that is going to be the short circuit current. What will you write in the denominator for this? 1 by GM plus 1 by GM. So it is going to be 0.5 GM. Are you getting? 2 by GM, inverse of it is GM by 2. 2 by GM, inverse of it is going to be GM by 2. Now, this is a gate question. I don't know why the examiner has given. Now he says that this I naught by V in is nothing but this voltage or this current, you can take it as IC, and this is VGS, this is ID. So he says I naught by V in is nothing but BJT is there and a MOSFET is there. You can write I naught by ID into ID by VGS, because VGS is V. What is the relation between collector current and emitter current? Collector current by emitter current is going to be beta by beta plus 1. Am I right? So he says this is beta by beta plus 1, which I hate it, right? Beta by beta plus 1 is what? Is the same current is flowing, but in the options he has given beta by beta plus 1, and ID by VGS is nothing but GM1. So the right answer for this is beta by beta plus 1 into GM1, right? What is beta by beta plus 1? It is almost 1 only, because beta is large. Am I right? 100 by 101. And this one we have already calculated. This I naught is same as ID1, and V in is same as VGS1. So what is the solution for this? GM total is going to be I naught by V in. It is going to be ID1 by VGS1. It is GM1. So 4 options were given: GM1, A, GM2, 0.5 GM1, 0.5 GM. 4 options in the gate paper. GM1 is the right answer, right? GM1. I naught by V in is ID1 by VGS1 is GM1. So the overall, so what did I tell you in this cascode amplifier? Cascode. Can you see the statement in cascode? The overall transconductance of the cascode amplifier is equal to the larger transconductance of the CE amplifier, CE or CS. This is CG. So who decides the transconductance is the CS amplifier or the common emitter. Yeah, a student, he raised a doubt the other day, right? Why you are taking GM1 for the telescopic cascode? Do you remember the telescopic cascode which I have drawn like this? I had NMOS here. So we have taken the half circuit and we wanted to calculate the gain. Yes or no?
Yes.
So this is suppose M1, this was M2, this is M3 and M1, M2, M3, M4, this was M5 in that, M6, M7 I believe. Am I right? So for this, if you want to calculate the voltage gain, AV, then you can treat this whole thing as a box. This GM total is going to be I naught by V in when V naught is 0. When V naught is 0. So what we will do is we will have to short circuit. We will have to short circuit here and then inject I naught. I naught. This is M3, M1. So what is the overall transconductance? This is going to be your ID1 by VGS1, which is nothing but GM1. So first step is over, GM1, right? Because we have injected a current here. The second step, this is step 1.
Okay.
The step 2 says that you have to calculate R0. R0. So what is R0 here? For calculating output resistance, your input should be grounded. Here we have to calculate R0. Then I told you it is like simple two resistors, up one resistor, down another resistor. And this R0 is going to be Rx parallel with Ry. This Rx is Ry. So what is R0? R0 is going to be Rx parallel with Ry.
RX.
What is Rx here? This is M5, M7. We have found the Rx as what value? GM5 R05, R07. And what is M7, M3 and M1? It is GM3 R03 into R01, right? And the last step is AV. AV is minus GM into R out. It is going to be minus GM1 in parallel with GM5 R05 R07 parallel with GM3 R03 R01. So like that also you can do, right? So many ways are there. See, when I do more than one way, you find which is simple for you. Are you getting? And it is always better you learn more than one way, right? So many ways are there. Imagine a current and write, or calculate the short circuit transconductance, and then calculate the output resistance of the amplifier, and then finally you can combine them, right? The short circuit transconductance into the output resistance. So that becomes the voltage gain. So this is a nice way of calculate. So finally, what is our MOSFET for this? The small signal, the complete MOSFET small signal model is what? This one. This is V in. This is GMV in, and this is R0. See, this is my small signal model for 4 MOSFETs. 4 MOSFETs. For 40 MOSFET also, this one is the small signal model. where GM is GM1, R0 is that value. So finally your output is going to be minus GM into R0. Are you getting?
Okay. Tau two plus tau two.
Okay. Now we can go for some doubt session.
Hello, sir.
Yes.
Hello.
Yeah.
Sir, 5F, sir.
Huh?
5F. Not this one, sir. First, you wrote and
Acha,
oh,
first one. I don't know where is it. Wait. Oh my God, everything is zigzag here. What you will ask? How to remove this, sir?
no idea.
Somebody was telling undo and all that.
Sir, here V2 by V1 equal to 1. How we got that, sir?
Where V2 by V1? This is common drain amplifier, no? Common drain is nothing but common collector. Gain is 1.
Okay, sir. Sir, and this new slide, sir.
Venkat, can you hear me? Venkat, can you hear me? See, we'll find a way to remove this. Or is it not possible?
Sir, and the new slide, sir. In the new slide, sir.
You
Another
want
doubt.
Okay, please.
Yeah. Tell me.
13F.
Hey,
13.
Yeah.
Sir, here can you explain this V2 by V1 by Vs once?
V1 by Vs, sir.
Yes, sir.
Here, can you see this here?
Yes, sir.
So the input resistance here is R pi, no? R pi I put here. This RF parallel. So these two are R2 and this is R1. Voltage division rule.
Yes, sir. Okay.
Do you remember voltage division rule?
Yes, sir. Yes, sir.
R2 by R1 plus R2.
Yes, sir. Got it, sir. Forgot that.
Hello, sir.
Yes.
Sir, can we go to 21F?
Yeah.
Sir, problems we are doing in last two classes, normally V0 by Vn equal to something resistance by something resistance.
Yes. That something resistance by something only. This also.
Sir, why you are choosing this method, sir? That method is comfortable, na, sir, for us.
It's okay. See, if you want only one method, then I will do only one.
Sir, can you tell this problem with the previous?
Yeah, with that method, what is V0 by Vin? V0 by Vin. There is something here by something, no?
Yes, sir.
Here in this loop, there is GM1, no?
Yes, sir. GM1.
Yes or no?
Yes, sir.
Negative sign because phase shift is there.
Phase shift.
Output resistance you have to calculate here, R naught, that's all.
Sir, but we are not considering the Terli effect, no, sir.
Early effect we are considering, that is why R02, no? The R02.
2 parallel with R0.
R02 plus 1 plus GM to R02 into R01.
One.
That you have to put here.
It's R0 plus R02 parallel
This is
R0
1 by this loop, no? So you will write 1 by GM1.
GM. Yes, sir.
Here output, that's all. Same thing only.
Here we are getting 1 plus GM1.
This is minus GM1 into R out. R out is nothing but what? R02 plus
Plus
1 plus GM to R02
into R0.
into R01. Yeah.
Okay, sir. Sir, how we can know that, sir, by doing that method and this method? Anyway, we
No,
can.
no, no. All are same only. I like this method, so I am calling it as an elegant way. I like it personally because why I like it. See, certain things you like and you don't know how to explain it, right? Something like that. See, suppose a problem like this is given. With that method, you will do it, but I like because I can challenge people to do this problem using what effect, early effect, and I can give them probably a day for them to do it, but they cannot do, right? If you put R0, it's very difficult for them to do. But if I short here, then my GM1, my transconductance is going to be 1 by the denominator. What is denominator? RE by alpha
Yes, sir.
plus RB by beta plus 1 by GM, no?
GM.
But my R0 is going to be this parallel with this, no?
Yes, sir.
So it's going to be RC parallel with this R0 plus 1 plus GM1 R0 into 1 plus GM1 R01
1.
into RE parallel with what? Here R pi is there. R pi and RB will be in series.
Yes, sir.
R pi RB R pi plus RB divided by 1 plus beta.
1 plus. Yes, sir.
If you do by small signal, I tried almost 3-4 pages. I'm getting too many unknowns. This equation 5 substituted in equation 3, equation 2 substituted in equation 1. Keep on doing. Finally, you'll feel right. So then I thought, okay, even V0 by Vin, see here, V0 by Vin, you're directly writing, no?
Yes, sir.
What your denominator you're writing, numerator you're writing. Here, denominator is step 1, denominator.
Yes, sir.
Step 2 is numerator. What is the problem I'm saying?
Yes, sir.
Are you getting?
Yes, sir. Yes, sir.
The same denominator, numerator is being divided into 2 steps.
2 halves. Yes, sir.
Yeah.
Sir, can you go to 21F, sir? I want to take screenshot.
Yeah.
Okay, sir. Thank you, sir.
Oh.
23F. Yes, sir. Good evening, sir, by the way.
Yeah, tell me.
So in here, why didn't we, when we are calculating V in, why aren't we considering VBE1 and
VBE1.
jumping? Yeah.
The first transistor input is given at base. Output is taken at emitter. It is an emitter follower. An emitter follower or common collector amplifier, gain will be 1. So this Vx is V in actually. So the other way of doing this is, or please 0.7 is only for DC analysis. VB means there is a resistor here. Okay, it is AC analysis we are doing. So this Vx itself is V in now. This voltage and this voltage are same. Can you see?
Yes, sir.
Gain is 1. Common collector gain is emitter follower. The output at emitter follows the input at base. So this
So
is
we
Vx
have to
is
keep
V.
in mind that it is emitter follower circuit, whatever it's in front of us.
How do I know it is an emitter follower? Then you have to see where the input is given and where you are observing the output. And you
So
can also
this-
see that the collector is connected to supply here. Common collector.
Okay.
So whatever you give V in, the same V in will appear here. 0.99 times of V in will be here.
Okay, this problem doesn't appear when we are calculating just for one MOSFET or one BJT, right? We are directly taking VGS, sorry.
This is VGS only. This is VGS1. But here, this is here the current is IB. This current is 1 plus beta times of this value, no? Here. So this value is much larger than complete Vin will be dropped here at Vx. This is called the emitter follower. The output at emitter follows input. Common collector gain is 1. This Vx is almost Vin. So when this Vin is here and your I naught is this, I naught by Vin is only GM2 directly. If you say, no sir, I don't want to do directly, I want to do I naught by Vin as I naught by Vx into Vx by Vin, then the procedure I've given you here. Do you want to know this procedure?
Yes, I got it. But when we are directly intuitively doing it and we want to consider just the Vin part and then the I naught part, then
Yeah, the complete Vin is here, that's all. This Vin is here. Q1 you can remove. I naught by Vin is nothing but IC2 by VB2 is GM2, that's all.
there I got. Okay.
Are you getting?
So VGS. So why are we considering VGS? That's what.
No, it's not VGS. VB is BJT, no?
Yeah.
VB, not VGS. VB.
Okay, so it is an emitter follower. That's why we are not considering VB in one, and also there is a RPi there.
Yeah, here there is an RPi. RPi is much larger, no?
Okay. And so
Okay, I'll give you one more idea here. Suppose somebody is here. Somebody is here, okay, in the middle. Can you see his face?
yes, sir.
Okay, now this guy sees this side and this side.
Hmm.
When he sees this side, there is an alpha by GM, he sees emitter. When he sees this side, he sees an RPi here. And you applied
sir.
Vin. So common collector completely will transfer here. Vx is Vin.
Okay. Now I got it.
So complete, because the complete signal is here, no? That is why its gain is
Yes,
1.
sir. Okay. And so the previous slide 5F, the previous slide 5F. No, so
Yeah.
not this one, the one that got messed up.
Oh. Now how to remove this?
So there's an undo button in the left, bottom left. You can undo things.
Okay, if you can help me out.
Yes, sir.
Yeah, tell me how to do this. Now it's saved, huh? We cannot do
It
anything.
is saved now. You can't undo, yeah. So 5F.
You can make changes and again save it.
Yes, sir. Here we are in this question. C.
Oh, can we?
now
There's an
C
undo
and
here.
can-
What should I do? Undo?
Yes, sir. Keep on undoing it. Then. Unless.
So go to last
So
page
this-
and
this-
erase it. Erase
No,
the
sir.
last page. There is content. All these content are from the last page.
All this content are available in last page here.
Yes, sir. This calculation of gain part.
All these pages have the same content.
So there is one eraser icon, if you can see.
100 pages
it
have this
is-
content. 100 pages you want me to do eraser? Huh?
No, sir. Just the one that started this thing.
Okay. No, see, this is a problem. I should have learned all this before coming.
Yes, sir. So just directly go to 5F.
Okay,
Yes, I don't
5F.
know how to do.
Tell me.
So how are we calculating C in here?
Scene for first one or second one?
Yes, sir. First one.
Scene for first one, that is an emitter follower, no? So your output
Yes.
and input are same, 1. So CF multiplied by 1 minus 1, 0. No scene.
Okay.
Emitter follower gain is 1.
So when can you split that using that Miller's effect?
That's what I'm saying,
thing
no?
that we
CF
use?
multiplied by 1 minus V2 by V1.
Okay, so it's
V2 by V1 is 1.
okay. Got it. Thank you so much, sir.
Yeah.
Hello.
Hello, sir. Hello, sir.
Hello.
Hello, sir.
Yes.
Sir, can you explain me, sir, the output impedance calculation of the cascode amplifier using BJT, sir? Same slide, I think 11th one, 11F.
This one.
Yeah, yes, sir. The left one, yeah, with RC.
Output impedance you want, huh?
Yes, sir. Like you, sir, draw any cascade amplifier and BJT, sir.
Oh, that calculation we have already done, no?
Yes, sir. I didn't get that, sir.
No, this R naught you want.
Yes, sir. R naught.
Ah.
Actually, in your calculation with R naught, RC was not there. So
Here there is R naught. You want to calculate from here, no?
yeah, but there is a RC also on the first one. There's a
Here RC is there, but I put an arrow, no? I'm seeing only down. RC is the load.
yeah, but like earlier calculation in earlier calculation.
Yes, my dear. If my arrow is here, it all depends where I put my arrow. If my arrow is here,
Yes, sir.
then I have to take RC parallel with this. Then it is the same value.
Okay.
But if I'm using this also somewhere in some IC, there is cascode only, no? Here today now you have connected RC as the load. You can have two PNPs in the place of RC.
Yes, sir. Correct.
Then this is the load now. The upper portion is the load. The lower portion, the output resistance is GM2 R02 into R01. It has increased, no?
Yeah, yes, sir.
Yeah.
Yeah, but like if we calculate the gain, sir, with like if we are calculating the gain, for example, we are giving some input and we are taking output. Sir, in that case, RC will be there for this circuit also, right? For that
Obviously, because the gain is a function of the load, no?
Yes, sir. Yeah, correct, sir. Sir, one more doubt, sir. Sir, in telescopic circuits, sir, you have yesterday you have discussed and today also you have discussed. Sir, can you please again calculate the R naught, sir? I didn't get that R naught. Output
And
impedance.
RX parallel with RY, yeah?
Yes, sir.
Yeah. Tell me.
Yes, sir. For example, from
This is
above-
like this, no? Here this is ground. This complete lower portion is RY, upper portion is RX.
Yes, sir. Correct.
Then what is R naught? R naught is going to be RY parallel with RX. Am I right?
Yes, sir.
So what is RY? Here you have M3 and here you have M1. So if you have if you have a MOSFET with some resistor R and there is an R naught here, the calculation of R out is R naught plus K times of R. This is a calculation.
Yes, sir. Correct, sir.
What is K? K is going to be 1 plus GM R naught
Yeah, correct, sir.
into R. Am I right?
Yes, sir.
Now in the place of R, I have put another R naught here. Which is R01. This is R02. So this in the place of R I have to substitute. R02 plus 1 plus GM2 R02 into R01 I have to put.
Yes,
Then it is R02 plus R01 plus GM2 R02 R01. This value is very large.
we can-
So I have approximated to GM2 R02 R01. Are you getting?
Yes, sir. Correct, sir.
Yeah.
Hello, sir.
Yes.
Hello, sir.
Hello.
Actually,
Hello.
hello.
Yeah,
Sir,
tell me.
for RY, sir, can you?
RY upper part.
Yes, sir.
Same R03, R04 like that you have to do. See, R naught is always from drain terminal, no?
Yes, sir. But
Upper
above,
portion is also drain, no? P and P.
yes, sir. Yes, sir.
This is also again drain. Wherever drain is there is R naught only, no? Like this you have to go.
Okay. If there's if above circuit is like instead of drain, it was
Source, then alpha
source
by
side.
GM, 1 by GM will be there, no?
Yeah, yeah, sir. One more thing. Sir, one more doubt is there, sir. Sir, in the third circuit, I think, uh, 16th or 17th page of this one, there is a series resistance RE or RS, I think, and we have to calculate the GM, sir.
GM calculation.
Yes, sir.
This one. This one.
No, not sir. This one. Not this one. Previous, I think. Second.
So these
program,
are all the
sir.
GM calculations.
Previous, sir. Previous. One more. Yeah. This one, sir. Yeah. So in this we have, sir, we have known that while calculating the voltage gain, then we have said the source resistance divided by alpha. RS plus 1 by GM, like that we write. But
Yes.
Here, if we want with the equation, sir, how do we get that like in terms of ID into RS plus 1 by GM?
You have to write KVL. VGS. This is ID, no? You have to write Vin equal to ID VGS plus ID into RS. Then you have to take ID common. Then it is 1 by GM, because VGS by ID is GM, no? ID by VGS is GM plus RS.
Yeah. Got it, sir. Thank you very much.
Hello,
Yeah.
sir. Sir, page number.
Sir, actually, due to Miller effect, the
No.
capacitance it increases, right?
Miller effect, the capacitance will increase. When the gain is more, capacitance will be more. If the
Yes,
gain
sir.
is less, capacitance will be less.
Do the fabrication units use this effect and create larger capacitances?
Yeah, definitely. For frequency compensation in op amp, we are shy of using capacitors there. But
Yes,
if you want to make a multiple pole system into single pole, because first order systems are stable, no? Op amp will behave like first order only, because that large capacitor they will put for frequency compensation. So there they will use Miller effect, and that capacitor is put between the two elements, 2 points in a Darlington pair, intentionally.
Okay.
So fab units, people are already using it
Okay.
to make a small capacitor look as a big capacitor. You're right.
Hello, good evening, sir.
Okay,
Yes.
sir.
Sir, page
Sir,
number 8, sir.
in calculation of gain, why are we making capacitor open circuit, sir, in Miller effect?
See, I told you parasitic capacitors are already open for calculation for AC analysis.
Yes, sir.
Coupling capacitors are already short.
Yes, sir.
These shunt capacitors are parasitic capacitors. So if you open them, then only you will get gain. If you short them, see, I am having an amplifier. In parallel, there is a capacitor. Suppose this is an amplifier, this one amplifier. Parallel, there is a capacitor. If I short this, what will happen? Output will be zero, no?
Yeah.
What will you calculate?
Without shorting it, why can't we consider its reactance, sir?
To consider its reactance, you have to open circuit and calculate RTH, no?
Okay. Yes, sir.
Yes or no?
Yeah. Yes, sir.
You calculate R Thevenin or R equivalent, then tau is equal to R equivalent into C.
Got it.
3 dB is 1 by tau. You're right.
Correct, sir.
Hello, sir. Good evening, sir. Sir, can you please open 8F, sir? Sir, yesterday's class 8F, sir.
Yesterday,
Sir, I was having doubt in yesterday's class. Sir, and I am having one common doubt, sir, like a difference between V bias and V in. What is the difference?
V bias. V bias is DC point. V in is AC.
Okay.
Biasing voltages are static voltages, DC voltages. V in is a AC signal.
Okay, VCC and VBAS both are same, sir.
Yes, you're right.
Okay. Sir, page number 8F, sir.
Tell me.
Sir, here, sir, not this one, sir. I think next page, 9F. Yes,
This
sir.
one?
Here, why we have not took that symmetry, sir? We can take symmetry also, right, sir?
Symmetry also you can take. This is one more method. Symmetry you take. If you take symmetry, what will happen? You will get V0 in the middle, no?
Yes, sir.
But you want right side, so that value you have to divide by 2. That's all.
Okay.
See, simple. 25 plus 475 is there, no, in the denominator?
25. Yes, sir.
Can you treat 25 plus 475 as X?
Yes, sir.
Then another 475 plus 25, you can treat it as X, no?
Yes, sir.
What is X plus X? 2X, no?
2X.
So if you take only one, you'll get X, and then you have to divide by 2. Same answer you'll get, no?
Okay.
See, are you getting?
Yes,
Writing denominator 2 times is taking half circuit and finally dividing it by 2 is the same thing.
Okay, sir. Actually, I was getting doubt like in right side the output we are not taking at base terminal. That's why we have not took.
No. Right side is that is why first differential amplifier you see. In that I told you left side is minus GMRC by 2,
Yes,
right
sir.
side is plus GMRC by 2.
Okay.
In between you take minus GMRC.
Okay, sir.
Are you getting?
Yes, sir.
Yeah. You take half circuit and you will get, see, you will write only 25 plus 475, no?
Yes, sir.
Then naturally the gain will not be 5, it will be 10. But
Yes.
in right side you are taking 10 by 2, you will do 5 only.
Okay, got it, sir.
Okay?
Yes, sir.
Yeah.
Sir,
Hello,
and
sir.
15F, sir. Hello?
Yes?
15F, sir. Sir, this I have not understood, sir. Hello?
Which one? Which part you have not understood? V0 by Vx or Vx by V?
Sir, V0 by V in, sir.
No, V0 by V. That means you have to split it into V0 by Vx, no, first?
Yes, sir.
V0 by Vx, can you see it is a common base amplifier? Can you see here?
Yes, sir.
Common base amplifier gain and common emitter amplifier gain both are same.
Yes, sir.
Gain is GMRC.
Yes, sir. Gain is GMRC.
Or you can imagine a same current RC by 1 by GM you will write.
Okay, sir.
V0 by Vx, what will you write? RC in the numerator by 1 by GM, no?
Yes, sir.
So it will be give GMRC. Is it okay?
Yes, sir.
Now we'll go for Vx by Vin. To get Vx by Vin, I told you in cascading, the first stage load is also the input resistance of the second stage.
Yes, sir. When we are seeing by Vx by Vin, we are seeing from Vx, sir.
From Vx, the amplifier 2, the second amplifier, CB is not a problem. When
Yes.
you are doing CE, you will always make mistakes, I told. Why? Because here, C, can you see here? When the last one we wrote minus GMRC. But
Yes, sir.
second one is minus GM2 into RC2 parallel with R by 3. Here.
Okay. Yes, sir.
And the first one, GM1 into RC1 parallel with R by 2. Can you see?
Yes,
That
sir.
is loading. So when you take Q1, you should also take the input resistance of the next stage. What is the input resistance of the next stage? It is emitter terminal alpha by GM. Can you see here?
Yes, sir. Alpha by GM.
So this is alpha by GM that comes in parallel with RC. So again, you have to write equation for common emitter. This common emitter, no? Gain.
Yes,
Common
yes, sir.
emitter gain is what? Minus GMRC.
Yes, sir.
But RC is in
Yeah.
parallel with?
Alpha by GM.
So see, I will write simple here. If I have RC here, what is the gain? Tell me. What is
Gain, first we need to take the resistance at output terminal, RC.
RC by 1 by GM minus GM RC, no?
Yes, sir.
So it is minus GM into RC. Suppose if I put RL, will this RL and RC come into picture? Parallel?
Yes, sir.
So it is minus GM into RC parallel RL, no?
Okay, sir. Now got it, sir.
That RL is nothing but this transistor, no?
Yes.
And the input resistance of this transistor is the RL.
Yes, sir.
Are you getting?
Yes, sir. Got it, sir.
Yeah. Now you have to put that
Sir,
alpha to GM.
okay, when we consider MOSFET, that term will be not there, right?
Which terminal? Emitter is there, no? Source 1 by GM will be there instead of alpha by GM.
Okay,
Gate
RC
terminal will not be
not
there. Gate terminal current is 0, no?
Okay, sir.
This is source terminal. Source terminal current will flow.
Yes, sir. Sir, and in today's class, I have doubt in 8F, sir, page number.
Fast here, so many people are waiting.
Yes, sir.
Yeah. This one I already, you said no.
In today's class, sir.
Today's class, sir. Tell me.
Sir, 9F. Sir, here I am getting confused. Like when we are short circuiting the capacitance and open circuiting, in some problems we are
No, this is AC analysis here. Gain. AC analysis we are doing. See, if I ask you what is the cutoff frequency, then you have to open circuit and see R equivalent. It is only gain you are calculating, no?
That is DC, sir. Cutoff means.
Gain, your mid frequency gain you are calculating. All the capacitors which physically are there should be replaced by short.
Okay, like if they will give in question, right, sir?
You calculate the mid frequency gain.
Okay, for AC analysis also they will give.
That is what is AC analysis. AC analysis means all the capacitors should be short. You have to find. For high frequency analysis, if one capacitor is given and you are asked to find the equivalent tau, then you have to remove that capacitor and calculate R equivalent there. That's all.
Okay.
See, if you short the capacitor and find tau means R into C, no? C will become 0.
Yes, sir.
So tau will become 0, no? Some tau will be there. So you have to open circuit and see.
Okay. Sir, on last doubt, sir. Sir, 24, sir. 24. Sir, this how you took, sir? I'm not getting Vx by Vn. How you took, sir?
No, forget about this. Just now you asked me this doubt only, no? Suppose there is an amplifier like this. This is a doubt we have already. What is V0 by Vin? V0 by Vin is nothing but RD by 1 by GM plus 1 by GM, no?
Yes, sir.
This denominator, 1 by this denominator is the transconductance.
Okay, sir.
These are transconductance.
Okay, sir.
So 1 by GM plus 1 by GM. It is 2 by GM. If you take it to the numerator, it is GM by 2 into RD. GM by 2, I am writing it 0.5 GM. That's all. What is that?
GM2. Okay, sir.
What you are
Okay,
right for input loop, no? That is the transconductance, 1 by of that value.
Yes.
Yeah.
Hello, sir.
Yes.
Sir, can you tell again 2 times how we are writing 1 by GM and 1 by GM?
Wherever VGS is there, current is same, no? Your ID.
Yes,
VGS is equal to ID into 1 by GM. By definition. GM by definition is ID by VGS.
Yes, sir.
GM, the definition of GM is transconductance. It is
Yes, sir.
output current ID by VGS. Are you getting?
Yes,
So
sir.
here Vin is having two VGS here in this loop. Can you see?
Yes, sir. Yes, sir. I got it.
So Vin should be written as VGS plus VGS.
Yes, sir.
VGS is ID into 1 by GM. Same current is flowing in a single loop. ID into 1 by GM plus 1 by GM.
Yes, sir. I got, sir.
Okay.
Ninth page, sir.
Yeah.
Sir, in this method, we have to short circuit capacitor, right?
Any AC analysis, you have to short circuit capacitor.
Yes, sir. If we short circuit capacitor, then base will be, but RF resistor is connected to base also. Then why we are connecting direct from
Base is already ground, no? This is G.
that
Ground
I
is G.
understood, sir.
This is G. This is G. They are all ground. This is G. Same only, no?
That I understood, but that RF resistor is connected to base now. That is what I'm.
That's what I'm saying. If you connect it to base, and if I tell you that RF is in parallel with RL, will you believe?
Okay, sir. Okay, sir. Fourth page, sir.
Yeah.
I am not understanding why we are writing C2 equal to 2C2 there.
Here the gain here. What is the gain of this amplifier? The gain is 2 times, no? First, I've already given you this. If you have a MOSFET like this and another MOSFET here, and there is a capacitor here, C.
Yes, sir.
Now, what is the gain of this amplifier? This is going to be C into 1 minus V2 by V1. No?
Yes, sir.
This is V1. This is V2. So for gain, the input resistance is the load. The load is going to be 1 by GM. V1, V2. The gain V2 by V1, common emitter gain is minus GM into RC, no, generally.
Yes, sir.
But here RC is not there. In the place of RC, there is 1 by GM.
Okay.
So the gain is minus 1.
Yes, sir.
So now you have to write C into 1 minus of minus 1. It is 2C.
Okay, sir. Okay.
Similarly, at output side, it is C into 1 minus 1 by V2 by V1. What is 1 by minus 1? 1 by minus 1 is again minus 1 only, no?
Yes, sir.
So it is again 2C only.
Okay, sir.
So the Miller capacitance multiplication has reduced. C Miller has reduced from where? Reduced from C multiplied by 1 plus GMRD, no?
Yes, sir.
To 2C. So if capacitance reduces, if the Miller capacitance reduces, tau will reduce, bandwidth will improve.
Okay, sir. Okay.
Are you getting?
Yes, sir. I got, sir.
Yeah.
Thank you, sir. Sir,
Sir?
please
Yes.
make us unmute one by one, sir. Everyone is shouting. I'm not getting chance only, but I'm raising hand first only. Tell,
Venkat,
tell
one by one,
to
Venkat,
co-host,
please.
at least from tomorrow onwards, sir. Tell to co-host that make us unmute one by one.
Okay.
Moreover, time also wasting, no, sir. Everyone is shouting like anything. That is
Yes.
Sir,
Yeah.
Thank you, sir.
Yeah.
good evening, sir. Sir, I am not able to understand the menu MOSFET. Can you please try to explain it briefly?
Which one?
Many elegant way of calculating voltage gain. What's the menu
See,
MOSFET?
basically a single MOSFET, small signal model has GM, no?
Yes, sir.
And it has an R0.
Yes, sir.
So now we are, for many MOSFETs, we are calculating one big GM
Yes, sir.
and one big R0. That is the idea.
Okay.
So how do you calculate a big GM and a big R0? What is GM? GM by definition is the short circuit transconductance.
Okay.
So we will take many MOSFETs and we will make V0 0 first.
Okay.
Okay. And then we will inject a current I0
Okay.
for many MOSFETs. So many MOSFETs are here like this. So you have to find V0 by Vin.
Yes, sir.
To find V0 by Vin, first step is V0 you make 0
Yes, sir.
and you inject I0.
Okay.
Then you will get capital GM.
Yes, sir. Okay.
Then you calculate the output resistance of this R0 here
Okay.
by short circuiting voltage source. Generally, resistance means current source is open, voltage source short, no?
Yes, sir.
Then
Okay.
finally, last step is minus GM into R0.
Okay. Sir, basically, we are treating many MOSFET as one MOSFET.
Now you got it. Many
Yes, sir.
MOSFET, small signal model is this now. GM, Vin.
Okay. Small GM is
with
big,
R0.
capital GM, basically.
This
Nothing
one is
else.
for many MOSFET. This one is for many MOSFETs. Instead of, otherwise, if you try to be bookish, what people used to do, they used to draw one for chota MOSFET, for one MOSFETs, small GMV in, again
Yes.
another small GMV in, again small GMV in. Can you do it 8 times, sir?
No, sir. Okay.
Now you got it, no?
Yes, sir. Basically, we are combining every MOSFET into one. We are treating it as one MOSFET.
Like calculating the overall short circuit transconductance and overall output resistance.
Okay.
Then you multiply it. That means the effort that you put for one MOSFET and the effort that you put for 10 MOSFET is same.
Okay. Sir, it means only that we are treating 10 as one. We can
That's
also
all.
say that.
This is for 10 now. This is
Yes,
for 10.
sir. Yes, sir.
That is why I called it elegant.
Okay. Yeah.
Not elegant.
Yes, sir.
Thank you.
Yes. Thank you, sir.
Hello, sir.
Yes.
Sir, frequency response of cascode లో డౌట్ ఉంది సార్. 5F పేజ్ అనుకుంటా సార్. అది అంటే అక్కడ బ్యాండ్ విడ్త్ ఇంక్రీజ్ చేస్తున్నావు కదా సార్, అంటే టౌ రెడ్యూస్ చేయాలి.
టౌ రెడ్యూస్ అయిపోయింది.
3 టౌలోని అన్నిటికంటే అంటే బ్యాండ్ విడ్త్ ఇంక్రీజ్ అంటే అన్నిటికంటే ఇప్పుడు T1 + T2 + T3 లోని అన్నిటికంటే ఎక్కువ వాల్యూ ఏదైతే ఉంటుందో టౌ ఆల్మోస్ట్
ఇక్కడ ఏమీ ఎక్కువ లేవు, అన్ని తక్కువే ఉన్నాయి.
ఇప్పుడు 1/GM ప్యారలల్ ఉంది కదా సార్. 1/GM ప్యారలల్ ఏదున్నా 1/GM అన్నిటికంటే తక్కువ వాల్యూ ఉంటుంది.
అవును, ఇప్పుడు RD ప్యారలల్ ఏదున్నా RDA అన్ని చిన్నగా ఉన్నాయి ఇప్పుడు టౌలు.
అంటే RD 1/GM RS ఈ మూడు కంపారబుల్ గా ఉంటాయి అంటున్నారు.
అంతే. అవి ఇంటరాక్టివ్ పక్కన ఉంటాయి.
అంటే జనరల్ గా మనం RS అంటే సోర్స్ రెసిస్టెన్స్ కదా సార్, RD అంటే లోడ్ కదా.
మీరు కంబైన్ చేసినా కూడా మీకు వాల్యూ అనేది చాలా తక్కువ. ఇప్పుడు ఎందుకంటే మీరు మిల్లర్ కెపాసిటెన్స్ ఒక సింగిల్ కామన్ సోర్స్ యాంప్లిఫైర్ పెడితే అక్కడ GMR0 వచ్చింది. GMR0 సపోజ్ 1000 ఉందనుకో, 1000 కెపాసిటీకి ఈక్వల్. అక్కడ ఇక్కడ 7 కెపాసిటీలే ఉన్నాయి.
అవును సార్.
సో బ్యాండ్విడ్త్ బాగా తగ్గుతుంది, సారీ పెరుగుతుంది. టైం కాన్స్టెంట్ తగ్గింది. టైం కాన్స్టెంట్ తగ్గడం అంటే స్పీడ్ బాగా పెరిగినట్టు.
స్పీడ్ అవును సార్. అంటే ఫ్రీక్వెన్సీ బ్యాండ్ అది ఇంకో డౌట్ ఉండేది సార్. అంటే ఫ్రీక్వెన్సీ రీచ్ పెరగడం అంటే అది స్పీడ్ పెరగడం అని చెప్తాం.
అంతే. టైం కాన్స్టెంట్. టైం అంటే ఇప్పుడు మీ ఊరికి వెళ్ళడానికి మీరు ఒకసారి 1 డే తీసుకున్నారు, ఒకసారి హాఫ్ డే తీసుకున్నారు, ఒకసారి 1 అవర్ లో వెళ్ళారు. అంటే స్పీడ్ ఎప్పుడు పెరిగినట్టు? 1 అవర్ లో వెళ్తే కదా. సో టైం కాన్స్టెంట్, టైం తగ్గితే స్పీడ్ పెరిగినట్టు.
థ్యాంక్ యూ వెరీ మచ్.
రైట్.
సార్ హలో సార్.
హలో
ఎస్
సార్, నేను వెంకటం సార్.
చెప్తున్నా
సార్ పిలిచారు కదా సార్, ఎందుకు?
అదే ఒక్కొక్కరిని అన్మ్యూట్ చేయండి అంటున్నారు. వీళ్ళందరూ ఒకేసారి అన్మ్యూట్ చేసేసరికి ఎవరు మాట్లాడుతున్నారో తెలియట్లేదు. ఓకే. ఎస్, నెక్స్ట్.
హలో, గుడ్ ఈవినింగ్ సార్.
యా
ఈసారి ఈ లాస్ట్ మనము ఈ ప్రాబ్లం చేసాం కదా,
చెప్పండి. హలో చెప్పండి.
హలో.
ఎస్.
హలో సార్, గుడ్ ఈవినింగ్ సార్.
యా.
ఈ లాస్ట్ మనము ప్రాబ్లం చేసినాం కదా సార్, ఏది బీజేటీ అండ్ మాస్ఫెట్ కలిపి.
అవును.
ఈ కరెంటు అవుట్పుట్ టర్మినల్ నుంచి I0 వస్తుంది, కానీ మనం మధ్య I0 బై ఐసి అది తీసుకున్నాం కదా సార్.
I0 అంటే ఐసి,
I0
ఉండేది ఐసి బై ఐడి, బీటా బై బీటా ప్లస్ 1.
నాకు ఈ మధ్యలో ఇంటర్మీడియట్ వాల్యూస్ ఎలా తీసుకోవాలని కన్ఫ్యూజ్ అవుతుంది సార్. కరెంట్ తీసుకోవాలా లేకపోతే ఎట్లా మనకి I0 బై ఐడి?
అది మొత్తం సిరీసేగా ఉండేది. వాడు ఆల్రెడీ డిఫైన్ చేశాడు ఏంటి, GM1 ఈక్వల్ టు ఐడి బై VGS1 GM1. వాడు GM1 ఇచ్చాడు, బీటా ఇచ్చాడు ఎగ్జామ్ లో. ఉన్నదే ఒక కరెంట్ గా. ఫస్ట్ ఆఫ్ ఆల్ ఆ ట్రాన్సిస్టర్ నువ్వు మాస్ఫెట్ అనుకుంటే నీకు GM1 వస్తుంది కదా. ఈ 4 ఆప్షన్లో GM1 ఎక్కడుందో అదే కదా ఆన్సర్.
ఎస్ సార్. అయితే ఇదంతా మనం ఇలా చేయకుండా ఇప్పుడు మనము గెయిన్ కనుక్కునేటప్పుడు వేస్తాం కదా సార్, డైరెక్ట్ న్యూమరేటర్ వాల్యూ వేసుకుంటే సరిపోతుంది.
కరెక్ట్ నాన్న. ఇప్పుడు నీకు పక్కన ఉంటే ఆ స్టేజ్ ఈ స్టేజ్ ఇది ఒకటే స్టేజ్ ఉన్నట్టుంది కదా, పైన ఉంది కదా ఇది.
ఎస్ సార్. సో ఒకటే కరెంట్ పాస్ అవుతుంది కాబట్టి
సైడ్ లో వేరే స్టేజ్ లాగా ఉంటే I0 బై VX అట్లా రాయొచ్చు. దీని పైనే ఉన్నప్పుడు అదే కరెంట్ వస్తుంది కదా అంటున్నా.
ఓకే సార్. సార్ ఇంకొకటి సార్, ఇప్పుడు మనము ఇది చేయకపోయినా మనం ఇప్పుడు గెయిన్ రాసేటప్పుడు మనం ఆ కింద డినామినేటర్ ఒకటి రాసుకుంటే సరిపోతుంది.
అదే ట్రాన్స్ కండక్టెన్స్. కరెక్ట్.
సో మనం ఈ అంత అవసరం లేకుండా అది కూడా అలా కంఫర్టబుల్ అయితే అలా కూడా చేసుకోవచ్చు.
ఇప్పుడు మీరు చూడండి, ఆ డినామినేటర్ M1 కి రాస్తున్నారు కదా మీరు, GM1 ఆ 4 ఆప్షన్ లో ఏది GM1 ఉంటే అదే కదా ఆన్సర్.
సో పైగా ఎట్లాగో లోడ్ అయిపోతుంది మనకి.
అంతే అంతే.
ఓకే సార్, థ్యాంక్ యూ సార్. థ్యాంక్ యూ వెరీ మచ్.
నెక్స్ట్. నెక్స్ట్.
Hello, sir.
Yes.
Sir, 7 has been.
Next.
Hello, sir.
Yes.
7 of page number. 7.
Hello.
7, sir. 7.
Yeah.
Sir, in this CX and CY, how we take, sir?
CX is the input capacitance, no? Miller effect.
Miller effect. C3.
CX is that the Miller capacitance due to C3.
Okay, sir.
And CY is the Miller capacitance at output. And CX formula is what? CX is C3 into 1 minus, can you see here?
Sure.
This formula. V2 by V1 is already there, minus GMR2. You substitute, that's all.
CY?
CY is output side. C multiplied by 1 minus 1 by V2 by V1.
Okay.
Okay.
సార్ వన్ మోర్ డౌట్ సార్, ఈ జేఫెట్ డిసి మనకి అసలు లేదా సార్? అంటే మనకి
సిలబస్ లో లేదు, తీసేశారు.
ఓకే ఓకే సార్, థ్యాంక్ యూ వెరీ మచ్ సార్. ఈ ఆసిలేటర్స్ అంటే మనకి ఇట్లా ఇవి కూడా 555 ట్రైమర్ ఇవి కూడా తీసేసారు కదా సార్ మొత్తం?
టైమర్ కూడా లేదు నాన్న.
ఓకే సార్, 555
పర్పస్ ఐసీ కాదు కదా అది. స్పెసిఫిక్ ఐసీలు అన్ని తీసేశారు. IC 723 కూడా ఉండేది ఒకప్పుడు, IC 7805 అవి కూడా ఉండేవిగా. ఆ రెగ్యులేటర్లు అవన్నీ తీసేశారు.
సో మనకి ఇప్పుడు ఈ
మిగిలింది ఏంటి ఇప్పుడు? డయోడ్, బీజేటీ, మాస్ఫెట్, ఆప్ యాంప్, జీనార్, అంతే.
అచ్చా జీనార్. ఈ ఆసిలేటర్స్ సార్, ఈ ఆసిలేటర్స్ కూడా లేదు సార్?
ఆసిలేటర్ మరి ఆప్ యాంప్ లో చేయాలిగా.
ఓకే సార్. ఏ మన హార్ట్లీ ఆసిలేటర్ ఇవి ఉన్నాయి సార్ ఇంకా? ఓకే సార్, థ్యాంక్ యూ. అది ఫ్రీక్వెన్సీ రెస్పాన్స్ ఓపీఎం కిందకి వస్తుంది సార్ అది?
ఏ ఫ్రీక్వెన్సీ రెస్పాన్స్?
ఇప్పుడు మనకి ఇట్లా ఇప్పుడు ఆసిలేటర్స్ ఇవన్నీ మొత్తం అవన్నీ ఒమేగా క్యాలిక్యులేషన్స్ ఉంటాయి కదా సార్, అంటే
అవునవునవును, ఆసిలేటర్ చేయాలి క్లాస్ లో.
అది ఫ్రీక్వెన్సీ రెస్పాన్స్ కిందకి వస్తుంది సార్, ఓపీఎం ఫ్రీక్వెన్సీ. ఓకే సార్, థ్యాంక్ యూ వెరీ మచ్. ఈ ఆసిలేటర్స్ ఓపీఎం తోనా లేకపోతే ఎట్లా సార్, అది బీజేటీనా?
ఓన్లీ విత్ ఆప్ యాంప్.
ఓకే సార్, థ్యాంక్ యూ వెరీ మచ్.
రైట్.
హలో సార్.
ఎస్
సార్, ఇంకో డౌట్ ఉండేది సార్. అది డార్లింగ్టన్ కంటే ముందు ఒక క్వశ్చన్ చేస్తాం సార్. అది అందులోని ఆర్ఎఫ్ అంటే ఏమి ఇచ్చామంటే స్టేట్మెంట్ మిల్లర్ ఆర్ఎఫ్ హ్యాస్ నో ఎఫెక్ట్ ఆన్ వోల్టేజెస్ యాజ్ ఇట్ ఈస్ ఇన్ ప్యారలల్ అని ఏదో ఇచ్చారు.
ఎప్పుడైనా ఒక వోల్టేజ్ సోర్స్ ఉందనుకో, దాని ప్యారలల్ లో ఒక 100 రెసిస్టర్లు పెడితే అది అదే వోల్టేజే అంటున్నా.
ఎస్ సార్, బట్ అంటే ఇప్పుడు మనం V0/VS చేసినప్పుడు అదే లోడ్ రెసిస్టర్స్ బై సోర్స్ రెసిస్టెన్సెస్ చేస్తున్నాం కదా సార్. అప్పుడు అంటే మనం ఇప్పుడు ఫర్ ఎగ్జాంపుల్ ఆ క్వశ్చన్ లోని ఆర్ఎఫ్ ప్యారలల్ ఆర్ఎల్ ఉంది న్యూమరేటర్ లో, డినామినేటర్ లో RE/α ప్లస్ 1/GM ఉంది. కానీ ఇంకోటి ఇక్కడ RF/1 - V2/V1 ఇది కూడా అంటే ప్యారలల్ లోకి వస్తున్నట్టుంది కదా సార్.
ప్యారలల్ లోకి వస్తుంది, ఎక్కడ వస్తుంది?
RE/α ఇంకా ఇది ప్లస్ 1/GM
సిరీస్ లో ఉన్నాయి కదండి. ఆర్బి సిరీస్ లో ఉందిగా.
ఆర్బి లేదు సార్, అంటే విఎస్
ఇవన్నీ సిరీస్ లో కదా ఉండేది
సార్. అది డార్లింగ్టన్ కంటే ముందు అనుకుంటా, ఒకసారి చూస్తారా సార్? అంటే
అలా కాదు నాన్న, నువ్వు చెప్పేది ఇదే కదా. ఇప్పుడు ఈ ట్రాన్సిస్టర్ ఉంది, ఇక్కడ ఒక వోల్టేజ్ సోర్స్ ఉంది, అంతేనా?
ఇంకా అంటే కలెక్టర్ ఫీడ్బ్యాక్ ఉంది సార్. అంటే ఆర్ఎఫ్ అది
ఇది ఆర్ఎఫ్ డివైడెడ్ బై 1 - V2/V1 నెగ్లెక్ట్ చేయమన్నా, అదేనా?
ఎస్ సార్, ఎస్ సార్.
నేనేమంటున్నా అంటే ఇప్పుడు ఇది ఒక 1 వోల్ట్ అనుకో, ఇది ఒక 1 ఓం అనుకో, దీన్ని థెవెనిన్ కట్టామనుకో, VTH ఏమైతుంది అంటే 1 వోల్ట్ అవుతుంది,
1 వోల్ట్.
RTH షార్ట్ చేస్తే 0 అవుతుంది. అంటే దీని ఈక్వలెంట్ ఇదే.
ఓకే ఓకే, ఓ ఎస్ సార్, RTH 0, అవును కరెక్ట్.
ఏం చేస్తున్నా రెసిస్టర్, ఏం చేస్తా అది జోలో పెట్టుకున్నా 1 వోల్టే, అది ఉన్నా 1 వోల్టే. ఇన్పుట్ రెసిస్టెన్స్ అయితే మామూలుగా చేంజ్ అయింది, గెయిన్ కట్టేటప్పుడు అది ఏం చేయలేదుగా. ఇంకోటి కరెంట్ సోర్స్ ఉన్నప్పుడు సిరీస్ లో రెసిస్టెన్స్ ఉన్నా వేస్ట్. అందుకే ఏమంటారంటే రెసిస్టర్ ఇన్ ప్యారలల్ టు ఏ వోల్టేజ్ సోర్స్ హ్యాస్ నో మీనింగ్, ఏ రెసిస్టర్ ఇన్ సిరీస్ టు ఏ కరెంట్ సోర్స్ హ్యాస్ నో మీనింగ్ అంటాడు.
ఎస్ అవును సార్, ఎస్ కరెక్ట్ సార్. థ్యాంక్ యూ సార్.
ఓకే
అంతే సార్.
Hello.
Yes.
Hello, sir.
Sir, in high frequency analysis, BJT you did, there you calculated gain is equal to minus GM RC, but there was RS also present. You have not considered that.
RS?
Yes, sir.
Which page?
Sir, I don't remember the page.
Minus GM into?
RC, sir, today you summarize the high frequency where BJT with RS at the base and RC at the collector. Sir, there you calculated gain is equal to minus GM into RC, but it should also contain terms like RS by beta also.
RS by beta, See, the problem is you have to first know where that capacitor is. Capacitor will have 2 plates, left plate, right plate. Left plate is at V1, right plate is at V2. Gain is only V2/V1. Gain is not V0/Vs. Capacitor will not know, no? Suppose I am having a 3-stage amplifier. 3 stage, 1 stage here, another stage here, another stage. And everywhere there is a capacitor, Miller capacitor. What should I do? Should I, for all these 3 capacitors, should I take V0/Vs? Or should I take V2/V1? I should take V2/V1, no?
Yes, sir.
Are you getting?
Yes, sir.
So there is RS here. Capacitor is here. So V2/V1. So what you have to do? V2/V1, you have to separately draw this here. Then you will realize it is minus GM into RC. Can you see?
Yes, sir. Why
you want to put RS by beta? RS by beta is for V naught by Vs calculation. But capacitor Miller effect is CF into 1 minus V2 by V1, not V naught by Vs. This V2 by V1 calculation you are saying, no?
Yes, sir. Yes, sir.
V2 by V1, this V2, this V1. Only GMRC is there, no?
Okay, sir. Sir, and in that many MOSFET one, that elegant method, you are writing AV is equal to minus GM into R naught.
Yeah.
Right? There is negative only when common source is there.
No. There is negative because we have injected a current into that device. This negative has come in the small signal model, no? Small signal short circuited current, Norton. We are injecting it inside, no? See, suppose a block is there. What is Norton equivalent? It is a short circuited current in parallel with resistance. Yes or no?
Yes, yes.
But the current direction is opposite.
Yes, sir.
Then how you will write Norton equivalent IS parallel with RSC? This
Yes,
is
sir.
I naught
Minus.
is opposite. So you should always have a negative sign in the final voltage gain.
Oh.
Okay.
So,
Let me come to your this thing. Suppose you have RE resistor. You are not doing common collector, then your GM will already have negative sign. Negative of negative will become positive. Don't worry.
Okay, GM will, if we will calculate, GM will have. So we have not done
negative
such
if you
question.
are calculating through emitter resistor.
So all the question we have done is of common. Oh no, we have done.
Common collect. Suppose here is there. See here. This one you want to do by that method, no? You are saying.
Yes, sir.
So this one you want to do by method. Step 1. Step 1, this point you have to short and inject a current. When you inject a current, this current is opposite to your IC. But IC by VB is GM, no?
Yes, sir.
So this is VB. So your I naught is opposite. So I naught by Vin is minus IC by VB. It is minus GM you will get. Okay. This minus of minus. Then output resistance you have to calculate. Here there is alpha by GM parallel with RE. So step 2, R naught is going to be alpha by GM parallel with RE. No? Then your overall gain is going to be minus GM into R out. Are you getting?
Yes, sir.
So
So
same.
for in GM1, how you did write negative sign? I didn't understand.
In GM,
Yes, sir.
GM by definition is IC by VB. No?
Yes, sir. Yes, sir.
This is short. Now this IC is in opposite of I naught. No?
Okay. Yes, sir. IC was almost equal to IE.
IE.
Yeah,
Then an alpha will come. You can do that calculation. What is it?
Yes, sir.
So see, your doubt is if it is through emitter, what will happen to the sign? Yes or no?
Yes, sir. Yes, sir.
You will. Then your transconductance will be negative, but final answer will be positive. So you don't have to worry.
Okay.
So the method is still elegant that way. Okay.
Okay, sir. Okay.
Yeah.
Sir, and one of the equation, it was written that the short circuit current gain. What does this mean?
Short circuit current gain means beta.
Beta means it is written determine 3 dB frequency of short circuit current gain of
So
BJT.
beta itself is a low pass filter, no? So what they're trying to say is this is a transistor. Its short circuit current gain is this IC by IB. Are you getting?
Yes,
IC by IB. But here you have C pi, no?
Yes, sir.
Here C mu.
Yes,
When
sir.
you short it, the C mu will come here.
Okay.
Are you getting?
Yes, sir.
Here C pi is here.
Yes, sir.
So now you have to do short IC by IB when VC is 0. So here you already have R naught.
Yes, sir. Yes, sir.
Here what is the tau? Tau is R into C.
Yes, sir.
So R naught into C mu is
So,
tau. Omega is 1 by tau.
So, but the answer arrived when I just added C mu and C pi.
Yeah, obviously, because this one is grounded, no? So obviously the C mu will come here. You're right. This is ground. No, short circuit means what? Your VC.
Yes, sir. Yes, sir. Yes, sir. Yes,
Your C mu will come here. Here there will be R pi. So your F is going to be 1 by 2 pi tau, which is 1 by 2 pi R pi into C pi plus C mu will come.
So that means short circuit current gain means we have to just short the. Okay.
Short B. That means beta itself is a low pass filter. See, this calculation is not needed actually. Who will give this? Manufacturer will give the short circuit current gain beta. Are you getting? This is also called F3 dB or FT something like that. We'll talk about this. Don't worry. In frequency compensation.
Okay, we will do this.
Yeah, frequency compensation I will discuss.
Okay. So what is wide band structure?
Wide band means something that has wide band bandwidth, more bandwidth, which will combat Miller effect, which will decrease Miller effect and increase the bandwidth. It's called a wide band amplifier.
So it can be band pass or low pass both.
No. Band pass means it will pass only a small frequencies. Wide band means, see, band pass means what? This is wide band pass, no?
Yes, sir.
Wide band means this.
So in between of the lecture, you were sometime using wide band frequencies.
Wide band means more bandwidth. That's a more bandwidth. It's called wide band.
Oh, means this
Cascode
will.
is a good example of a wide band amplifier.
Okay, sir. Sir, and there was one question where BJT was there, which was means base was connected to direct collector with a resistor. So have we done this
That we
circuit?
have done, no?
Sir,
Minus R2 by R1. Today we have done directly minus R2 by R1.
okay, that works like op-amp, that one.
Yeah. That one. This one, no? This is R2 R1.
Yes, sir.
Minus R2 by R1. That's all. In option 53K, 530K, something they have given 10 answer. Get problem.
So, like if we will remove that AC source, then same circuit, and the question was like, which of the following biasing will give the best performance in preventing?
See, biasing, all those are outdated. Nobody is biasing with voltage dividers.
So this type of question will not come.
This will come, but it used to come for our, what should I say, 15, 20 years back, it used to come. Because these days, biasing is only with transistor. Transistor will bias transistor. It's not resistor, this bias, that bias. Voltage divider bias is outdated, I told you, no?
Yes, sir. So, but there are many questions which are asking like...
Old is okay. Voltage self-bias is good. Of all the circuits, self-bias is good.
Yes, sir. But in all these answers, self-bias is not the correct answer. Like,
Yeah, because two feedbacks he has given. No, one collector to base, one emitter. So he says it is more stable.
Collector to base and emitter.
Emitter also one resistor will be there. Collector to base there, another resistor. He says this is more stable because more feedback is there. First of all, those kind of feedbacks nobody uses now. Are you getting? That is why last 5 years papers you see.
Okay, sir. Okay.
You will get idea.
Okay. So, and that increasing doping concentration and all, that all we will
EDC,
study in EDC.
Yeah.
Sir, and negative coefficient resistance and all, these are old question papers.
No. Old. What you do with that? Resistor negative.
Sir, in workbook, all the questions are mixed.
No, you do. Volume 2 you do. Volume 2. Volume 2 is written by me.
Okay, sir. Okay.
Are you getting?
Yes, sir. Sir, and stability question, stability factor.
You want, I will do it, but it's waste. If you want, I will do one problem, stability factor. Okay?
Oh, means these are all are outdated question type.
Outdated means in IES they might ask. Dou IC by dou IC not. For IES students, I will definitely do. Okay? One problem I will do is very simple. Dou IC by dou IC not we have to calculate.
Okay, sir. Okay. Thank you so much.
Okay.
Thank you.
Hello, sir.
Yes.
Page number 23. Sir, in this alpha by GM, GM equal to
Alpha by GM. This, don't write alpha by GM. R pi 2 by R pi 2 by alpha plus 1 by GM you write.
1 by GM.
You want to write like this, by alpha and 1 by GM.
Okay.
The same only.
With respect to emitter.
With respect to emitter I have written. This is with respect to corrector.
Why we neglect total, sir? Alpha by. Hello, sir. Hello. Hello, sir.
Yeah.
Sir, GM equal to GM to how, sir?
R pi is beta by GM, 100 times more.
That's my idea.
Yes.
24 expected. Sir, in this Vx equal to Vx by Vn, not wrong, sir. Vx by Vn.
Px by Vn.
No.
Yeah.
One,
input resistance is 1 by GM, no? Here I have written.
Yes, sir.
1 by GM by 1 by GM plus 1 by GM.
Denominator both emitters, sir.
Denominator 1 by GM1 plus 1 by GM2.
Okay. 26, sir. Page number 26. Sir, in this I naught by ID equal to beta by beta plus 1.
I naught by ID. Yes. IC by IE is beta by beta plus 1. Here I have written.
IE equal to beta plus 1 into IB.
IE equal to
beta plus 1 into IB.
Yes, but IC equal to beta IB, no?
Yes, sir.
So IC by IE is beta by beta plus 1.
Okay, sir. Thank you, sir.
Okay.
Hello, sir.
Yes.
Hello, sir. Good evening, sir.
Yeah.
Actually, the concept of improving the bandwidth is there, no, sir.
Yeah.
In that, the steps what you have done is I understood, sir. But how we are improving the bandwidth there, sir? I didn't get that.
Bandwidth equal to 1 by tau, no?
Yes, sir. But what you said in that tau is increasing only, no, sir. When the tau is
decreasing,
the
tau is decreasing, no? Capacitors have become 2C now.
Yeah,
Only 7 capacitors are there. 7 capacitors are there. One is 2C, almost 9C. But there the C into 1 plus GM into RD. GM into RD will be 1000 C. If only common emitter is there, the capacitor effect is going to get multiplied by 1000 times, no?
Yes, sir.
But here it is only after cascade, it's only 2C. Capacitance is reduced. Tau is reduced. Bandwidth will improve.
Yes, sir. Maybe after that, that I think so, sir. But in that, you said that the tau is increasing. So I felt that is also comes under that only.
No. Tau is reduced. Overall tau is reduced after cascade.
Okay. Yes, sir. We know that when the tau decrease means we'll get the bandwidth more.
You are
but
right.
In that time, yes, sir. Okay, sir. Sir, and one more thing. Sometimes you are considering beta and some other times you are not considering beta, no, sir.
Examiner will give beta infinite means don't consider.
So every time IC equals to V.
IC
The
equal
beta
to IE. Differential amplifier is there means mostly examiner will say beta infinite. IC equal to IE.
Okay, sir. Okay,
If he
sir.
gives, we
Thank
can
you.
consider it. Mostly will not give beta large. When circuits are bigger, no, he will say beta large.
Okay, sir. Beta large means we can do easily only.
Yeah. Because already circuit is big and he has given for 2 marks. So what you will do? Beta large. He will say.
Yes, sir.
Okay. Shall we stop for today? Anybody else?
Yes, sir. We can stop.
Yeah.
సార్ స్టాప్ చేసింది.
వెంకట్
సార్
అది 2 డాక్యుమెంట్లు ఉన్నాయి, నేను పంపిస్తున్నా వెంకటరెడ్డికి. ఒక దాంట్లో ఏమో ఒకటి పైన ఒకటి ఏవో వచ్చేసాయి, అవి ఏమన్నా తీయగలుగుతామా?
ఓకే సార్, ఒకసారి వెంకటరెడ్డి మాట్లాడుతున్నాను నేను.
రైట్. అది సూపర్ ఇంపోజ్ అయిపోయినాయి, అంటే ఇమేజ్ పడిపోయింది దానిపైన.
ఒకసారి పంపించండి సార్ వెంకటరెడ్డి, ఒకసారి నాకు పంపించండి.
రైట్.
ఓకే సార్.